Positive and negative. Opposites attract. It's a tale as old as time. Oh wow, there's a whole bunch of positives and a whole bunch of negatives. I wonder what's going to happen. Oh, they're mixing around and relaxing and... Well, look, they end up in a nice little arrangement. Very nice. A crystal is born. This is just a simple collection of atoms, so take it as a grain of salt, but crystallinity in general is the relaxation of atoms into their low-energy configuration. But we don't just have to look at crystals. We have technology. So suppose we have a whole row of positives up top and negatives down below. Now, if we shoot a positive test particle through, it's going to be pushed away from the positives and attracted towards the negatives, so its path is going to curve like so. Likewise, if we send a negative test particle through, it's going to be pulled towards the positives and pushed away from the negatives. It's kind of weird how the charges know where all the other charges are. I mean, how does that actually work? Is it like telekinesis? Like all the charged particles in the universe are talking to each other at a distance, telling each other how much to be pushed around and in what direction? That doesn't seem right. Whatever's going on here in this universe, you'd think that something at some place shouldn't just be able to push around something else in another place. So we come to the strange and inevitable conclusion that there must be some kind of a something throughout space and time, let's call it a field, that charged particles interact with. So in this example, suppose these stationary charges give rise to a vector field like so, with the vectors pointing away from the positive charges and towards the negative charges. Then, as we shoot our test particles through, the vector field is going to push them around in accordance with their charge. Positive charges will be pushed along the direction of the vector at each point in space, while negative charges will be pushed in exactly the opposite way, anti-parallel to the vectors at each point. Meanwhile, a particle without any charge will just float on by. It's like, yo, I'm not doing all that charge stuff. I'm just going to float on by. Okay, so electric fields are a thing. And also, if you've ever done the thing with the magnet and the iron filings, you can see that magnetic fields are a thing too. So for some reason, there are fields. And, electric and magnetic phenomena were actually known about since antiquity. Both the words electric and magnetic come from ancient Greek. Electric comes from the Greek word for amber, because amber has some cool static electric effects. And magnetic comes from a region of ancient Greece where people used to find these cool magnetic rocks. And for the longest time, these were just separate things. But later on, in the 1800s, as people got better at wielding electricity and playing around with magnets, it was discovered that the electric and magnetic fields are intimately related. Actually, they're two sides of the same coin, and they're locked in an eternal dynamic interplay. And when they splash around, that's what light is, as well as radio waves, X-rays, microwaves, and so on. So a wonderful picture began to emerge, where all of the electric phenomena, and all the magnetic things, and light itself, and even a whole bunch of invisible frequencies of light, all emerged as specific manifestations of more fundamental, more elegant underlying patterns. These patterns can be described mathematically. The patterns taken on by the electric and magnetic fields are encapsulated by Maxwell's equations, the 4 equations shown here. Each of these equations is cosmically powerful on its own, so if you equip yourself with all 4 of them, you'll be unstoppable. The 4 Maxwell's equations reveal to us the patterns in the electric and magnetic fields. But to do physics with these fields, we also have to know how they push around charged particles. And for that, we have the Lorentz force law, which tells us that charged particles will be pushed along the electric field, while they're going to be pushed in a swirly way around the magnetic field, depending on their velocity. In both cases, the direction of the force depends on the charge, with the field pushing on positive and negative charges in opposite ways. The four Maxwell's equations, combined with the Lorentz force law, comprise the mathematical framework of classical electromagnetism, which describes the electromagnetic phenomena to a very high degree of accuracy. In practice, one also encounters material properties, things like resistivity, which can be understood within the framework of Maxwell's equations and the Lorentz force law. Material properties, just think of those as things that emerge in the statistical limits of a very complicated condensed matter system. Well, anyway, so at the end of the day, it's all about Maxwell's equations and the Lorentz force law. And you can study this, and you can take classes on electrodynamics, and you can solve these differential equations in every which way, and you can develop an understanding of all these different electromagnetic phenomena in technology and in nature. But even if you become a wizard with the vector calculus, even if you become a sage with the Maxwell's equations, there's going to be a question that will keep you up at night, and you'll become obsessed with this question. And this question is, why is electromagnetism a thing? Because it feels like it's an expansion pack that you have to put on your worldview. Like, it's one thing, if you're learning physics, right? You learn about space, you learn about time, you learn about force and acceleration, and all of that kind of makes sense. You can kind of see that those things are things in the world. But then when it comes to electromagnetism, you're supposed to believe that there is such a thing as an electric field and a magnetic field, and the magnetic field is a pseudo-vector field, it's not even a real vector field, and these things interact and they flop around, and that's what light is. It's like, okay, hold on now. What? Like, why? Like, philosophically, why, right? Okay, so that's the question. And this entire video, the whole purpose of it, the whole everything we're going to do today, is in service of answering that question. Because that question does have an answer. And it's actually a pretty satisfying answer. Like, it's actually remarkably satisfying, the extent to which we can understand why electromagnetism is a thing. Now, the answer is simple enough to state. Why is electromagnetism a thing? The answer is because the Dirac field has local U1 phase symmetry. Simple as that, right? And it is simple as that. Once you learn the math, once you learn the physics, you see it really is as simple as that. But of course, okay, what does that principle even mean? What is the Dirac field? What is local phase symmetry? And how exactly does that principle imply electromagnetism? So that's what we're going to be talking about today. Here is a brief overview of what we're going to be talking about in this video. First, we're going to take it on faith that the Dirac equation has local phase symmetry. So we're going to go into what is the Dirac equation, what is phase symmetry, and then we're going to demonstrate why matter and antimatter have equal and opposite charge, why photons are massless with a 4-vector wave function, why the electric field exists as a 3D vector field, why the magnetic field exists as a 3D pseudo-vector field, why these electric and magnetic fields interact. We're also going to derive Maxwell's equations, so Gauss's law for magnetism and electricity, Faraday's law of induction, and Ampere's law with Maxwell's addition, as well as the Lorentz force law, and we're also going to see why electric charge is conserved. So as you can see here, we're going to be able to turn this simple principle about phase symmetry into electromagnetism, which is remarkable. I mean, this is going to be very profound. It's a beautiful topic. For better or worse, this topic involves some pretty sophisticated math and physics that you normally encounter for the first time as an upper division undergrad, and then contend with in a more serious way in grad school. So this video is going to be more hardcore than my previous ones, and so it might appeal to a narrower and more technical audience. But this subject matter is too beautiful not to talk about, so I have to make this video. Okay, so here's a brief list of the prerequisites that you'll want to be familiar with to get the most out of this video. First of all, you'll want to have some experience with classical electromagnetism. The reason being, this video is all about why electromagnetism is a thing, and so you have to know the what before the why is going to make any sense. So you'll want to have some familiarity with Maxwell's equations, Lorentz force law, electric and magnetic fields, voltage, magnetic vector potential. Basically, if you've taken an introductory class on electrodynamics, you should be okay for this video. Likewise, and this goes along with electromagnetism, you'll want to have a good understanding of vector calculus. At least you'll want to be comfortable with the idea of like a gradient, divergence, curl, flux integrals, that sort of thing. I actually am going to not get too mathematical in this video. Like, for example, I'm not going to get into differential geometry or fiber bundles, even though that kind of math does have some really interesting applications to the topic of electromagnetism as a gauge theory. My goal today is to teach you the main concept of how symmetry gives rise to electromagnetism, and I want to do that in the most accessible possible way. So I am going to be using the language of vector calculus because that's kind of the lingua franca of STEM people. And anyway, once you learn these ideas, you're always welcome to translate them into whichever mathematical framework you prefer. Also, you're going to want to have some familiarity with quantum physics. So you'll want to know the Schrödinger equation, the Klein-Gordon equation, the Dirac equation. And I only mean up to the first quantization. So you don't have to worry about second quantization. You don't have to get into the quantum field theory. Everything we're doing today is going to be first quantization, meaning quantum particles, but classical fields. So for example, psi is going to be the wave function of an electron. And even though the electron's position and momentum are these fuzzy quantum things, psi itself is going to be a field whose values are precisely defined at particular moments in space and time. And that is in contrast with quantum field theory, where psi itself becomes like a fuzzy field. But actually, quantum field theory is not necessary to understand how electromagnetism arises from symmetry, and so we're not going to do the second quantization today. And also, you'll want to have some familiarity with special relativity. So you'll want to be familiar with the concept of Lorentz invariance and the mass shell, which is the relativistic energy-momentum-mass relation. In particular, you'll want to understand how the mass shell relates to the Klein-Gordon equation, and how taking the square root of the mass shell gives you the Dirac equation. And if you like, you can refer to my videos on the Klein-Gordon equation as well as the deriving the Dirac equation for more information on that. In addition, there are some relativistic kind of mathematical things you'll want to be familiar with. So for example, the difference between a covariant and a contravariant 4-vector. You also want to be familiar with things like the 4 gradient, and just in general, being able to think in terms of unifying space and time, momentum and energy, probability flux and probability density, that sort of thing. So you want to have some exposure to special relativity as well. And I know, it's kind of a tall order to say, okay, you'll want to be somewhat familiar with relativistic quantum physics before getting into this video. But actually, a lot of these concepts are pretty accessible, and you can find them in the book Introduction to Elementary Particles by Griffiths. This book will get you up to speed on all of the quantum physics and special relativity concepts that we're going to use in today's video. This is actually one of the best textbooks ever, and I can't recommend it enough. If you're interested in these ideas, this is one of the best investments you can make. By the way, nobody's paying me to say that. I'm just speaking the truth. Anyway, in this video, if I say that an equation can be found in Griffiths chapter 7 or whatever, well, that's the book I'm referring to. Okay. Also, I should mention the conventions that we'll be using in this video. We're going to be using Gaussian units, which are the cleanest, most elegant units for exploring the theory of electromagnetism. So be aware this differs slightly from SI units. But the difference in units is not going to really make a profound conceptual difference, At the end of the day, you can always convert from one system of units to another. So, but yeah, today we'll be using Gaussian units. And also, we're going to be using the mostly minus metric, which is sort of the standard convention in particle physics. And the mostly minus metric is not as pessimistic as it looks, because we're going to have a positive time. Sorry. Oh, also, I should say, if you're not familiar with all of these concepts, don't worry. You might still get something out of this video. And you can always think of this video as a way of learning through immersion. And besides, when you're learning math and physics, it's often helpful to take a look beyond your current horizon to see what's coming up. And just remember that the concept we're talking about today is one of the most beautiful, most amazing concepts in physics. And but it is difficult, and that's okay if it doesn't make sense all at once. It's a big topic, So if you're not sure whether you're ready for this topic, just give it a shot. All right, let's get into it. So we're going to start with the Dirac equation without any electromagnetic field. So this corresponds to a particle that's chilling in the vacuum of space. And the equation can be written as I h bar gamma mu partial mu psi minus mc psi equals 0. Okay, now first and foremost, unlike the Schrödinger equation or the Klein-Gordon equation, which both use a complex scalar field for psi, in the Dirac equation, psi is a 4-component complex vector, which actually should be regarded as a pair of spinors at each point in spacetime. So psi is not a 4-vector. It's a bispinner. And it transforms differently under Lorentz boosts, but we're not going to go into detail on that today. And naturally, one wonders, why is it that psi is complicated like this? And the answer for that, as we saw in the Deriving the Dirac equation video, is that the defining characteristic of the Dirac equation is that it's first order in space and time, while also unifying quantum physics and special relativity. And the only way you can do that is to take the Klein-Gordon equation and really squish it down to be first order in space and time. The equation really does not want to do that because it's intrinsically, when you apply the mass shell and the quantum mechanical energy momentum operators, the thing that you get is sort of inherently the second order thing. But if you push hard enough, so hard that the commutative property of multiplication shatters, then poor little psi is going to get squished, and it's going to go from this complex scalar to this bispinner situation where the different components of it are going to be kind of spinning around. And that spin structure is actually necessary in order to accommodate the full range, the full degrees of freedom that we need in order to have a relativistic quantum physics, while at the same time describing the theory using only first derivatives in space and time. Now, in this equation, the gamma mu partial mu term uses the Einstein summation convention, where if an index appears twice in a single term, it implies that the term is summed over all values of that index. In general, by the way, Greek indices like mu and alpha and beta, these are placeholders for the numbers 0, 1, 2, or 3, 0 being time-like, and 1, 2, and 3 being like x, y, and z. Okay, now in this expression, we see the 4 contravariant gamma matrices, which are 4x4 matrices containing a bunch of zeros and some 1s and i's. These gamma matrices have the properties required to have a first-order differential equation, which uses the quantum mechanical energy momentum operators and also satisfies the relativistic mass-energy momentum relation, also known as the mass shell. Now, these partial terms are the partial derivatives with respect to each component of spacetime. And it's helpful to think of these as components of the 4 gradient, which you can write partial mu. And here, notice there's only one index, so we're not summing over. When you see partial mu, think of it as all possibilities for mu in a 4-vector. So partial mu, we can say this is partial 0, partial 1, partial 2, partial 3. And that is defined as the partial derivative with respect to x mu, where x mu with the mu upstairs is now actually the contravariant spacetime position, the 4 position. And if you look at Griffiths section 3.2, as well as equation 7.6, you can see more information on that. But for today, all we have to know is that the symbol partial mu corresponds to the 4-vector, which is 1 over speed of light times the partial derivative in time, and then partial derivative in x and y and in z. And as with all 4 vectors, the factor of the speed of light is just there to make the units the same for the time component as for the spatial components. So, in this video, when we see partial mu, that corresponds to that 4 gradient, think of that as the space-time gradient, and the individual components, partial 0, that's 1 over c times the time derivative, partial 1 is the x derivative, partial 2 is the y derivative, and partial 3 is the z derivative. Now, the signs in the 4 gradient are a bit confusing. Usually when a 4-vector has a downstairs index, that is, when it's a covariant 4-vector, the spatial components are going to have a different sign than the time components. But in this case, the covariant 4 gradient is actually made of partial derivatives of the contravariant 4 position. So the signs are actually all positive. Now, if you're not super familiar with the Dirac equation just yet, don't worry about it. We're not going to have to know everything about it today, just a few things. And we'll just have to visualize a couple of simple solutions to it, which is going to give us insight that we can then mathematically generalize to more complicated scenarios. So first of all, let's just go ahead and write out the Dirac equation like so, where we're going to go ahead and expand everything so you can see the gamma matrices and the derivatives and all that. Now you can see here that the Dirac equation says that a combination of first derivatives of psi, each one modified by a gamma matrix, equals psi itself multiplied by some imaginary valued constant. This equation has a rich landscape of solutions, but by far the simplest one is for a particle in free space, whose momentum is known to be precisely 0. Now, because the momentum is precisely known, And because this is quantum physics, what do we know about the position? Nothing. Nothing whatsoever. We know nothing about the position. And so when we solve for the zero momentum eigenstate, we should expect to find a wave function which is spread uniformly throughout space. I went into this in detail in my previous video on solving the Dirac equation for a particle at rest, but we'll briefly review the solution here as a segue into the next topic. So, we can solve for the zero momentum eigenstate by recognizing that it won't have any spatial gradients, since those encode momentum, and so the spatial derivative terms are going to vanish from the equation. Now we're left with something where there's just one time derivative and a gamma zero and an MC over H and a psi. Well anyway, if we write out the definition of gamma zero and show psi explicitly as a bispinor with 4 complex components, and while we're at it we'll multiply both sides by the speed of light, then we get this equation which can be thought of as an eigenvector-eigenvalue problem, and it admits 2 distinct families of solution. So first of all, we have the solutions for which psi1 and psi2 are non-zero, while psi3 and psi4 are 0. As it turns out, these correspond to electrons, and they have the form psi electron equals AB00 times the exponential of negative I mc squared over h bar times time. Now when you look at that equation, what you see is there's this bispinor, and the top 2 channels are occupied, so A and B, think of those as comprising a spinor. And then the time evolution of that thing is the same as we would expect to find in the Klein-Gordon equation. It's just a unit-length exponential that's vibing in time with the frequency of the mass energy of the particle divided by h bar. Likewise, there are solutions for which psi1 and psi2 are 0, while psi3 and psi4 are non-zero. And those are the positron solutions. So you can write them as 00 CD, for some arbitrary complex number, C and D, times the exponential of I mc squared over h bar times time. Now in both of these cases, A, B, C, and D are all just complex numbers, and they're typically normalized so that magnitude A squared plus magnitude B squared equals 1, and magnitude C squared plus magnitude D squared equals 1. And actually, you'll typically see this written as just a 1 symbol for a spinor in the top component or bottom component, but I'm actually going to write it out in terms of the complex components just so that we can really see what's going on. Now, the time evolution of these 2 solutions is very, very similar. Both are just phase factors which oscillate in time with a frequency mc squared over h bar, and the only difference between them is the way in which the phase goes around the complex plane in time. So the 2 solutions are oriented backwards with one another relative to time. And that is the fundamental and essential difference between matter and antimatter, as we're going to elaborate on later in the video. You don't have to take my word for it that these 2 solutions correspond to electrons and positrons. We'll demonstrate later in this video why that's the case, and why these have opposite charge. But for now, we should just notice that the structure of the Dirac equation gives us 2 completely different ways for psi to represent a particle with 0 momentum, which differ in their orientation in time. And this branching of the equation into these 2 different modes of solution, even though we've only demonstrated that for the very specific case of the eigenstate of a particle at rest, that branching is still broadly a factor of any conceivable solution of the Dirac equation. So if you want to Lorentz boost the solution and you get some non-zero momentum eigenstate, and then consider the set of all possible momentum eigenstates, and then you're just a Fourier transform away from whatever wavy waves you want. In general, you're going to have a solution which is either occupying the top 2 channels or the bottom 2 channels, with one tiny little nuance or caveat, which is that technically the top 2 channels and the bottom 2 channels, they do kind of bleed into each other just a tiny little bit, especially in the relativistic limit, but this can normally be ignored. But if you want to see an example where the 2 sides can kind of bleed into each other, look up the Darwin term for the hydrogen atom. That's something we'll get to in the future. By the way, I have not forgotten about hydrogen part 3. In fact, the last few videos, including this one, is still kind of a tangential note between parts 2 and 3, so I will get back to that someday. Hopefully someday soon. Okay, so the Dirac equation branches into these 2 different modes of solution, matter and antimatter. Let's go ahead and consider the electron solution first, and you'll notice that the spinor AB can be thought of as some linear combination of the spinors 1, 0 and 0, 1, because AB is just A times 1, 0 plus B times 0, 1. Now the spinor 1, 0 corresponds to a purely spin-up electron, while the spinor 0, 1 corresponds to a spin-down electron. So if the electron has spinor AB with magnitude A squared plus magnitude B squared equals 1, that is normalized, then it's in a superposition of spin states, and when its spin is measured, there's going to be a magnitude of A squared probability of measuring it spin up, and a magnitude of B squared probability of measuring it spin down. And it's one of the weird quantum mechanical things that when you measure the spin, it's either spin up or spin down. Hey, I don't know, that's just one of the weird things about reality. You can think of the electron as containing 1 bit of spin information, so it's either up or down. It's super weird, but anyway, it is what it is. So, now here's something interesting to think about. Look at that exponential term, which is just a unit-length phase factor. That thing is going to swing around A and B in the complex plane, but it's not going to change the size of A or B. So if an electron is chilling in free space with zero momentum, its spin state is not going to change over time, in terms of likelihood of measuring spin up or spin down, but instead its components are just going to rotate around in the complex plane. Let's put some visual insight on this. We'll use the same flag animation as in my previous spinor video, where on the right half of the screen we see 2 components of the spinor, and on the left we'll see the flag that this corresponds to, because as we saw in the spinor video, each unit spinor evolving under some SU2 transformation can be mapped to a flag which represents a 3D rotation SO3 element. And in fact, SU2 double covers SO3, so for each flag orientation, there are actually 2 spinors corresponding to that, which only differ in the complex plane picture by a minus sign. And to transform one possibility into the other, you want to do a 360-degree rotation, that is a class 1 rotation. Anyway, see my spinor video, see also the paper An Introduction to Spinors by Andrew M. Steen for more information on this flag diagram. You can also download this Python code on my Patreon. And that's something I want to get better at. You know, on Patreon I post the PDF video notes for these videos, but I also want to start posting more animation codes, so that those of you who are supporting my channel can actually get your hands on some real, genuine, for real codes that not only make these pretty animations, but also use the math behind them. So hopefully that'll be a good learning resource for you. Shout out to all my supporters on Patreon. I'm really grateful for all of you. Okay, well, so remember what we're doing here is looking at a zero momentum eigenstate. That is, a state that has no spatial variation, no spatial dependence. And so we don't have to imagine these states as an entire field throughout space, because instead we can just imagine what a single spinor would look like and watch it evolve in time, and then we can imagine that the whole wave function is just this spinor vibing like this at everywhere in space. So for example, what I'm showing here now is the electron solution for A equals 1 and B equals 0, that is, a spin-up electron. You can see that as the complex phase factor rotates the spinor in the complex plane, the flag rotates around its axis. Imagine this flag rotating at every point in space. That's the Dirac field for a spin-up electron with precisely zero momentum. Of course, it's not actually a flag. The flag is just a way of imagining the spinor, which makes a lot of its algebraic properties much more visually intuitive. By the way, shout out to Kurt Jaimongel for introducing me to these flags. For years, I had to feel my way around the Dirac equation algebraically, but these flags have given me a whole new perspective on the math. So instead of lines of algebra, with these flags you can just imagine it and jump right to the solution, or at least an outline of the solution. So I can't overstate how much this has improved my life. So thank you, Kurt, sincerely. And everyone watching this, please consider checking out Kurt's YouTube channel, Theories of Everything. If you like my videos, you'll probably enjoy his channel too. Oh, something else about this flag. Look at the way it's rotating. Take your right hand and curl your fingers around the way the flag is going around. Your thumb will point up along the flagpole, and that's why they call it spin up. So right now, in your mind, before you see it on your screen, I want you to imagine what the 0-1 solution is going to look like. That is, the spin-down electron. How will the flag be oriented? And how will it be rotating? And what will the spinner look like in the complex plane? Are you imagining it? Are you examining the solution with your mind's eye? Are you visualizing the solution? Okay, let's see if you were right. Boom, there it is, a spin-down electron in the zero momentum eigenstate. It's the same as spin up, but down. Apply the right-hand rule again, and now your thumb is pointing down. And again, as the complex phase factor rotates the flag around its axis in time, it does not change the orientation of the axis. So remember what I said earlier about how the spin state is going to remain the same over time for an electron at rest in a vacuum. So then what about some superposition of spin up and spin down? How about, for example, 1 over root 2, 1, 1, which has an equal probability of being spin up or spin down. By the way, the square root of 2 is just there to normalize the spinner. So, what do you think this is going to look like? How will the axis of the flagpole be oriented? And how will it be rotating? Well, here it is. You can see that the flagpole is halfway between up and down, and as before, the rotation in the complex plane simply rotates the flag clockwise around its axis. But wait, why is the flagpole pointing in this particular direction and not some other direction while still being horizontal? Isn't there actually a circle of possibilities for a spinner that's equal parts spin up and spin down? Well, yeah, actually there is. And it all has to do with the complex phase difference between the two components of the spinner. See, both components will pick up the same time-evolving phase factor, but throughout time there will be some phase difference between them, and that phase difference can be anything between 0 and 2 pi. So notice that multiplying the whole spinner by some complex phase isn't actually going to change the relative phase difference between the two components. And as it turns out, that phase difference between the two components is going to track with that azimuthal angle of the flagpole. So for example, here's the state 1 over root 2, 1i, which is the same amount of spin up and spin down as before, so it's still horizontal, but now it's pointing 90 degrees away from the previous state, because the previous state with 1 and 1 had no phase difference between the components. But now, with 1 and I, there's a 90-degree phase difference between the components. And so the flag is rotated 90 degrees relative to what it was before. So in light of this, what do you think the state 1 over root 2, 1, negative 1 would look like? In that state, the 1 and the negative 1 have a 180-degree phase difference. And sure enough, the flag points oppositely as the 1, 1 state. Cool, well, how about 1 over root 2, 1, negative I? Can you see this spinner in your mind? Can you imagine how it looks? Can you mentally do this quantum physics? Well, there it is. So the phase difference between the components of the spinner has a visual interpretation. It plays a role in determining the flagpole orientation, and specifically, it determines the angle around horizontally, the longitude, if you will. Azimuth is probably a more technical word. So on this topic, what if the superposition of spin states is not equally balanced, but is more of one than the other? So, for example, 1 over root 5, 2, 1, which is mostly spin up, but kinda spin down. And here again, the root 5 is just a normalization constant so that the spinner has unit magnitude. So, given everything we've talked about so far, which way should the flagpole be pointing? Notice that 2 and 1 have no complex phase difference between them. So the flagpole looks like this. And by the way, this has an 80% chance of being measured spin up, and a 20% chance of being measured spin down. Because 2 squared is 4 and 1 squared is 1, so it's 4 to 1 odds of being spin up. And that doesn't come as a surprise, because if you look at how the flag is pointing, it kind of makes sense. Man, I love these flags. Such a useful way of looking at the math. Okay, a couple more examples here. So, what about 1 over root 5 to I? Well, same as before, but now with that 90-degree phase difference. And so the flag is rotated 90 degrees. You see how this all fits together? Okay, so isn't this neat? Neat little algebraic structure. By the way, you put a bunch of different flags in there, and you can rotate them all in the complex plane, and in the three-dimensional view with the flags, each one is just going to rotate around its axis. So this math is so cool. I love it. I think this is just remarkable. And what's amazing is that this spinny behavior, this rotating behavior, was not put in by force, or by fiat. It's an inevitable consequence of writing a first-order equation which is both quantum mechanical and relativistic. Dirac, isn't that correct?
That is correct, yes. And that forced me into a different kind of equation, and this different equation brings in the spin of the electron. It was very unexpected to me to see the spin appearing in this way. I thought one would first get a satisfactory theory of a particle without spin, and then one would proceed to a more complicated theory of the particle with spin, but it turned out differently. The simplest kind of particle does have a spin.
Now then, what about the positron solutions? Well, in terms of the different possibilities for the flagpole orientation, it's exactly the same ideas as before. All the ways the flagpole can be oriented are encoded in the relative sizes of the components of the spinner and the complex phase difference between the components. Then that whole flag just spins around, same as before, but in the opposite direction due to the sign change in the exponential. So, you often hear positrons described as electrons that are moving backwards in time. I think that description is misleading because, if you drop a grain of salt in a glass of water, it dissolves as time goes on. Well, if you drop an anti-grain of anti-salt into an anti-glass of anti-water, it's still going to dissolve as time goes on. Okay, so there's no time traveling going on here. So I like to say that a positron is just an electron that goes the other way, because that's just ambiguous enough to kind of convey the message. And also for things like dissolving and like thermodynamics and statistical mechanics, you can see that an ensemble of things, if you reverse the direction of all the little constituents, the behavior at the macro scale can still be the same. Okay, so now we've seen the connection between multiplying a Dirac spinner by a complex phase factor and rotating the flag about its axis. And the key points there is that when we multiply psi by a complex phase factor, all we're doing is turning the flag. Now, there are two things that we should keep in mind. First, there's an angle doubling between the complex phase angle and the flag rotation angle. So a phase factor of e to the I theta is going to rotate the flag by an angle of 2 theta. And this pertains to the fact that SU2 double covers SO3. So if we sweep the phase factor all the way around in the complex plane, a full 360, then the flag will rotate twice during that process. And that's just part of the weirdness of fermions with their half-integer spin. But for today, we can just notice this detail in passing and otherwise ignore it. The factor of 2 doesn't really matter for today. And now the second point has to do with the difference in time evolution between matter and antimatter. As we've seen, these two options are oriented backwards relative to each other in time. But it's important to notice that this time reversal arises due to the reversal in the direction that the time-dependent complex phase factor evolves in the complex plane, and that the reversal is not due to a difference in the connection between the complex phase factor and the flag rotation. In other words, if we go clockwise in the complex plane, the flag is going to rotate like an electron solution. And what makes positrons go the other way is that they go counterclockwise in the complex plane. It's not that a complex phase factor rotates positron flags the other way. It's that the complex phase factor itself is going around the other way in time. And so the connection between the complex phase angle and the direction of the flag rotation is the same in either case. Okay, so now let's explore the concept of local phase symmetry, which means that if we apply an arbitrary local phase transformation to psi, nothing observable will change. So first, let's look at what a local phase transformation is, what that means, and what it does. And then we'll talk about what it means for nothing observable to change. So first, to look at what a local phase transformation is, we should look at not just a single flag, but a field of flags, at least a two-dimensional slice of the Dirac field, since we'll want to see how things change over space when we transform our wave function. And looking at a full three-dimensional picture would be a little bit too cluttered, but that's okay. 2D is good enough for now. So here on the left, we have a spin-up electron. And on the right, we have a cross-section in the xy plane of the zero momentum eigenstate for that electron. And notice that we're looking at it from below. So the base of the flagpole is closer to your eyes, and the top of the flag is pointing into the screen. So you see how the view of the single flag kind of maps onto the view with the flags in the field, and you can kind of see how, like, the orientation there? Okay. Our eyes are in the negative z-axis looking up. Okay, so what we're looking at here is just a very particular cross-section of a very specific and simple solution of the Dirac equation. So we have to remember that the electron's wave function can actually be much more complicated than this. And in general, the amplitude can vary, so imagine that the flags will be larger in some areas and smaller in others, and infinitesimally small throughout most of spacetime for a localized particle. But fortunately, just by looking at these simple eigenstates, we can get some valuable insight about how psi is affected by local phase transformations. And this will give us a mental image that will be a great starting point that we can warp and transform as needed when mathematically generalizing from this specific case to more general situations. Okay, so let's get into it then. What exactly is a local phase transformation? Well, it's simply the act of multiplying psi by some phase factor e to the I theta, where theta is a phase angle that can change in both space and time. And that's what makes the transformation local rather than global. So a global transformation is just multiplying by a constant phase factor everywhere in space and time, which is basically just a redefinition of the phase angle. And that's not very interesting or physically meaningful. But a local phase transformation, that's a much stronger transformation, because that means we can change the phase by a different amount here versus there, now versus later. And so this gives us infinitely many ways to mess around with psi. And remember, multiplying psi by a complex phase factor has the effect of rotating the flag about the flagpole. So these local phase transformations are going to twist the flags around arbitrarily in space and time, depending on how we define our theta field. But the transformation is not going to be changing the orientation of the flagpoles themselves. It's just going to be turning the flags around their flagpoles. Okay, so let's look at a specific example. So here on the left, we have the zero momentum eigenstate of a spin-up electron. Oh, and let me say this, for everything we're about to look at, the direction of the spin really doesn't matter. These local phase transformations, because they're going to turn the flags around their flagpole, but they're not going to change the flagpole direction, it doesn't really matter which spin we want to look at, and the reason I chose spin up with the XY cross-section is just so that we can have a nice, easy view of a flag going around. And the reason I'm picking this particular orientation is so that the way the flag goes around looks a lot like the time evolution of the phase factor in the complex plane. Okay, so then let's define our theta field for the local phase transformation. For starters, we'll keep it simple, and we'll just use a field where the phase angle varies along some direction with a constant rate. And because phase is a circular thing, if you vary it at a constant rate, it'll look wavy and periodic. So that's what the phase field is going to look like. Here, I'm using colors to represent the complex phase in accordance with our usual color map, and I'm also using arrows to represent the complex phase angle. And this view is technically a little bit redundant, but I hope it's helpful, especially when you're comparing the color of the flags to the color of the complex phase factor. Well, anyway, one more thing to note about this phase field is that theta is the phase angle, and that can be whatever we want it to be, but e to the I theta, the thing that we're actually plotting here, that complex phase factor, is always going to have unit length, right? It's an element of U1, so the amplitude or the magnitude of the elements in the phase field are all going to have the same size. And that's important because then when we multiply this field on psi, it's not going to change the size of psi. It's just going to slap on a complex phase factor. All right, so given our eigenstate psi and our phase field e to the I theta, what is the transformed psi going to look like? Well, it'll look like this. Oh, look at that. Pretty neat, huh? So check out what's happening here. On the left side, we have our unmodified psi, so that's just our eigenstate. Then we have the phase field that we're going to use to transform that psi. And on the right side, we have what appear to be these propagating waves. But notice that all this is basically just the phase gradients put onto the wave function, and bear in mind the angle doubling and all that. And then all of that's being animated just by the fact that the flags are turning around at some constant rate. And so imposing a phase gradient on psi gives us these propagating waves. And by the way, this is basically what a non-zero momentum eigenstate looks like. Okay, in the non-relativistic limit, but the relativistic limit, it gets more complicated with the way spinors transform. But anyway, it is how it looks, okay? When you put in this kind of a phase transformation on psi, it's no longer a particle at rest. Now it's a particle in motion. Okay, so we kind of messed up psi because this is changing things, right? This idea about local phase symmetry, that you can do local phase transformations and nothing observable will change, well, that's not looking too good because here we're doing this local phase transformation and we seem to have put some momentum into the electron. So, so that seems weird. Why is it like that, right? That kind of goes against our deeply held belief that the Dirac field should have local U1 phase symmetry. So, okay, so we're going to talk more about that in just a moment. But while we're here, let's explore this a little bit more. So, of course, if our theta field varied along some other axis, then we're going to see momentum appearing along that direction. Okay, so we notice that there's a connection between phase gradients in space and momentum. Okay, well, the question comes up, what about time? Let's have a phase field where, for now, there's no spatial stuff going on, but let's just rotate it in time and see what happens, right? Well, this is going to have the effect of either speeding up or slowing down the rate at which the flags rotate. Because, it's how it is. I don't know what words to put into it, but the phase transformation is either going to be helping the flag along or it's going to be slowing it down. And bearing in mind that the rotation rate of the flags is directly proportional to the energy of the particle, we can see that there's a connection between phase gradients in time and energy. Now here I should point out that in reality, these flags rotate extraordinarily fast. For an electron with a mass energy of 511 keV, the flags are going to spin around like 100 quintillion times per second. So the phase transformation I'm showing here, whose frequency is of a similar order of magnitude as psi, is actually super aggressive, like many, many orders of magnitude more so than anything that's relevant to what we'll be talking about today. So in case you were wondering what happens if the phase transformation goes so fast in time that the flag's rotation direction starts to go the other way, the answer is don't worry about it. That corresponds to preposterously extreme scenarios that are well beyond the scope of this video. Alright, well, what if we do some crazy phase field that changes in both time and space? Well, it's the same basic idea about energy and momentum and phase gradients in time and space, but it's just like more wild and complicated. But at the end of the day, the way theta is changing in space and time will affect the distribution of how the flags are turning around, and that's going to give rise to these momentum and energy changes in the wave function. Okay, so the key insights of these animations are that when we do a local phase transformation on psi, gradients in the theta field, both in space and in time, will change the momentum and energy of the particle respectively. This can be stated more elegantly from a relativistic perspective. The Fourier gradient of the theta field changes the Fourier momentum of the particle. Well, okay, so it actually seems like psi really doesn't have local phase symmetry, right? Local phase transformations are able to mess up psi in all kinds of different ways, creating a whole four-vector of a mess in the particle's energy and momentum. Yeah, so the idea that the Dirac field doesn't actually have local phase symmetry, at least not on its own, that's actually true. And we're going to get back to that in just a moment, but while we're here, let's see how antimatter fits into the picture. So for this animation, what we have here is an electron's wave function on the left and a positron's wave function on the right. In both cases, we're looking at them from the bottom up, with the flags pointing into your screen. Now the expert viewer will say, hey, if we're charge conjugating, then shouldn't we also reverse the flagpole direction? And yeah, that's a good point. But as mentioned earlier, what we're looking at now doesn't have much to do with the spin orientation, so we can get away without having to flip the positron flagpole around, because this way it's easier to compare the two plots, especially as it relates to time reversal. Now if that bothers you and you want to flip the positron around, you're welcome to imagine the positron flags flipped the other way, but then, since they'll appear to be turning clockwise like the electron, you'd have to carefully parse out the nuances about the complex phase time evolution versus the phase to flag rotation direction, and with a lot of mental effort, you'll end up at the same conclusion, but just, in a more circuitous route. So the way I'm showing it here is easier to look at, so let's just go with this, and then we'll recognize later that the conclusions we come to don't actually depend on the spin state of the particle, so this is okay, everything's fine. Oh, and so now in this animation, we're just going to plot the transformed wave functions on the same plot. So, for example, First, we'll use a phase field that's just the number 1 everywhere, and we see the untransformed wave functions of both the electron on the left and the positron on the right. Now, if we hit the fields with a spatially varying phase field, check this out. In the electron field, we see the same waves as before. But in the positron field, they're going the opposite way. What? Wow. Why are they moving the opposite way? Well, because the flag rotation is brought to life by a time-dependent complex phase factor, which goes the opposite ways in the complex plane for electrons versus positrons. And so the same change in the complex phase is going to have an opposite effect on the time evolution of the flag. And this is easiest to see from the orientation where the flag rotation looks just like the complex phase evolution, which is why we're showing it here with the flags all pointing into the screen. Well, anyway, at the end of the day, the fact that electrons and positrons are oriented backwards in time relative to each other means that the same phase gradient is going to affect the momentum of the particle in an equal and opposite way. Okay, and now of course the question is, what about time? Well, if we look at a phase field that's uniform in space but varies in time, we find, unsurprisingly, that it'll speed up one of the wave functions and will slow down the other. So how the phase transformation changes the energy will also be equal and opposite whether we have an electron or a positron. And again, if we use some crazy phase field, we get crazy results. But this thing about equal and opposite disturbances in psi is still true. So that's basically all I'm going to say about antimatter today. From now on, when talking about psi, we'll assume it's an electron. And as we construct electromagnetism from local phase symmetry, all we have to do is remember this picture about matter and antimatter being disrupted in equal and opposite ways by local phase transformations, and we'll see and we'll be able to intuit that electrons and positrons have identically opposite electromagnetic behavior. That is, they have equal and opposite charge. Alright, so now we've seen what a local phase transformation is, and how it affects the Dirac field psi. And based on what we've seen about changing the energy and the momentum of the particle, we strongly suspect that the Dirac field does not in fact have local phase symmetry. That is, local phase transformations are not going to leave all observable quantities unchanged, because it's going to mess with the energy and momentum, and that's just like how it seems to be. But to elaborate on this, we need a precise definition of what it means to leave all observable quantities unchanged. And for that, we turn to the framework of Lagrangian mechanics. The Lagrangian way of looking at physics is based on the principle of least action, which says that there's some quantity S, called the action, which will naturally be minimized as things happen in nature. So then, if we can write an equation for the action in terms of our field variables, then we can see what has to be true about our fields in order for the action to be minimized, and in that way we can derive the laws of physics for our system. When working with fields that vary in space and time, the total action of the system is calculated by adding up, integrating over spacetime, a quantity, fancy L, which I like to think of as the activity of the system, by which I mean the infinitesimal amount of action which at some point in spacetime is happening right there and right then. The word activity feels right, as a sort of intensive version of the extensive action, but anyway, fancy L is not actually called the activity, it's called the Lagrangian density. Oh, but everyone calls it the Lagrangian. So think of the Lagrangian as a seed that grows into the laws of physics. Later in the video, when we derive the inhomogeneous Maxwell's equations, we'll see how this works in gory detail. But for now, the only thing we have to recognize is that the Lagrangian encodes the laws of physics in a condensed format. And this gives us a great way to define what it means for some transformation not to change any observables. If the Lagrangian isn't changed by the transformation, then neither will the laws of physics, and neither will any observable quantity. So now we can define local phase symmetry very precisely. The Dirac field has local phase symmetry if, and only if, its Lagrangian remains unchanged by any arbitrary local phase transformation. So, to answer the question of whether the Dirac field has local phase symmetry, all we have to do is write out the Dirac-Lagrangian, which depends on psi, and then apply a local phase transformation to psi, and see if the Lagrangian changes. In the interest of time, I'll just write out the Dirac-Lagrangian here, and I won't go into exactly why it has this form. But I'll point out that this Lagrangian directly implies the same good old Dirac equation we've been working with, and uses all the same characters and ingredients, so the form should not be too surprising, and we're not sneaking anything in here that's electromagnetic. Oh, actually, there's one ingredient here that we don't see in the Dirac equation, and that's this thing psi bar. So psi bar for the Dirac equation is much like psi star is for the Schrödinger equation. Psi star is just the complex conjugate of the scalar psi, but when psi is a bispinner, we have to upgrade that notion to the Dirac adjoint, which is psi bar, and you can make it in 3 easy steps. Step 1, you take the column that is psi and flip it over into a row. Step 2 is you complex conjugate every term in psi. And step 3 is you multiply the last 2 terms by -1. And there you have it, that's psi bar. Okay, but other than that, all the symbols in the Lagrangian are the same as what we've already used for the Dirac equation, and so we can go ahead and start exploring this Lagrangian. Okay, so now what we're going to do in order to see how the Lagrangian is affected by a local phase transformation is we're going to replace every psi in the equation with a transformed wave function e to the I theta times psi, where again theta is this phase field, this phase that can change in space and time. And by the way, now in this equation, psi does not have to be a simple eigenstate. It can be a totally general solution to the Dirac equation. So this goes beyond the particular examples we've been looking at, but those examples will still help us make sense of this math because they give us like a visual starting point. Okay, so to evaluate the transformed Lagrangian, we're going to substitute the transformed psi prime with e to the I theta psi. Now first, if we look at the psi bar term, what we can do is we can pull the complex scalar e to the I theta out of the bar by recognizing that when you take the Dirac adjoint of something, you can pull out a scalar by taking its complex conjugate, and the complex conjugate of e to the I theta is e to the negative I theta. Then, for the psi prime on the right side of the equation, we're going to distribute that through to the left, so we're going to let the foregradient act on e to the I theta psi, and we're going to have that mass term mc squared times e to the I theta psi. And next up, we want to clean up that foregradient term. So when you're calculating the foregradient of e to the I theta psi, we can apply the product rule, and first take the foregradient of e to the I theta multiplied by psi, plus e to the I theta times the foregradient of psi. So that's just your normal application of the product rule. And so now if we evaluate the foregradient of e to the I theta, and we're going to keep things topologically trivial, then we end up with an expression I times e to the I theta times the foregradient of theta. So now what we can do is if we look at both of the terms in that expression, we see that they both have an e to the I theta, so we can factor that out. Now, if we look at the term of the transformed Lagrangian, you see those blue terms I'm highlighting, the e to the I theta times I? And you see how that multiplies through the foregradients of e to the I theta psi. So let's bring that together, and we'll let the e to the negative I theta cancel out the e to the I theta, and we'll multiply through by I. And we see that the product of that blue and yellow term ends up being simply negative psi times the foregradient of theta, plus I times the foregradient of psi. So now we can write the transformed Lagrangian as shown simply by replacing the blue and the yellow terms with this green term. And while we're at it, you'll notice that the mass term with the mc squared e to the I theta psi, we've taken out the e to the I theta by distributing through that e to the negative I theta. So there's no more e to the I thetas. Okay, and next up what we're going to do is simply rearrange the equation as shown. So here I've color-coded the characters so we can kind of see like how it is. So basically we've switched up the equations and kind of moved things around and massaged the equation a little bit, but we haven't actually really done anything other than that. We're just rearranging terms. And the reason we're rearranging terms like so is because now look at the left side. Look at that left term. Psi bar I h bar c gamma mu partial mu minus mc squared psi, that is the original Lagrangian. Wow. And so that means that the transformed Lagrangian is our original Lagrangian minus h bar c partial mu theta psi bar gamma mu psi. And so if we assume that term is not zero, then we see that the transformed Lagrangian is actually not the same as the original Lagrangian, because it's picked up this extra term, and so no, the Dirac equation very much does not have local U1 phase symmetry. Shoot, that contradicts the one thing that we were hoping would blossom into electromagnetism. Darn it. So, we have two options here. Option number one, we can give up. To do that, just turn off the video. Okay, well now that all the quitters are gone, option number two is we do whatever it takes to do what we gotta do. This means being creative, thinking outside the box, just whatever has to be done. So, what exactly is the problem that we're trying to solve? Well, we want the Dirac field to have local phase symmetry, but based on what we just saw, we can say confidently that the Dirac field does not have local phase symmetry on its own. Wait, on its own. The Dirac field does not have local phase symmetry on its own. But what if we added something to our model of the universe? Something that might exist, that could play a supporting role in giving the Dirac field local phase symmetry. Is there any way to do that without it just being some kind of mathematical trick? Is there any physically realistic way in which the Dirac field might be given local phase symmetry? Well, we know exactly how the Dirac field fails to have local phase symmetry, because we can say with precision exactly how the Lagrangian is messed up by some arbitrary local phase transformation. If you multiply psi by some arbitrary phase field, then the Lagrangian will be changed by a factor of negative h bar c partial mu theta psi bar gamma mu psi. So if we want to give the Dirac field local phase symmetry, we need to find a way to counteract that term for all possible phase transformations. At first, this seems overwhelming because of the infinite variety of phase fields we can use to mess up the Lagrangian. How can we possibly correct for all of these possible things? But that infinite variety is actually helpful because it means that the solution to the problem has to fit the problem like a glove fits a hand. In other words, we don't have to think about any particular phase field and come up with some complicated, contrived solution which accounts for multiple different categories of phase transformations. No, we just have to completely erase negative h bar c partial mu theta psi bar gamma mu psi for arbitrary theta. And so that's the answer right there. That's what we have to do. We have to erase that term. So to give the Dirac field local phase symmetry, we simply redefine its Lagrangian to include a term which is equal and opposite to the mess that the local phase transformation creates. This new modified Lagrangian is manifestly unaffected by local phase transformations. You can see this by starting with the field theta equals 0, in other words, no transformation, in which case the term we've added goes away, and it's just the Dirac Lagrangian. But then if you switch to some arbitrary theta field, you'll find that our new term precisely cancels out the mess that otherwise would have been created. So that's great. We know exactly how we need to transform the Lagrangian in order to give the Dirac field local phase symmetry. But now the problem becomes, how on earth is this a legitimate move? I mean, this feels totally like we're cheating or hallucinating or just making up some nonsense that just so happens to solve our problem, but has no underlying reason or justification to it. If we're being good physicists, we should call shenanigans on this. We can't just go, redefining things just because it's how we want it to be when it's not. If it is, if it isn't. What? Well, okay, let's investigate this in more detail and see what we've actually done here and see if there's a legitimate way to tell a convincing story to justify why this is an acceptable move and not just a bunch of nonsense. Okay, so this is kind of an exercise in rationalizing the irrational, but it'll actually turn out to be true and very deep. So, okay, we have our Lagrangian, and this is the Dirac Lagrangian plus this other thing that we're adding on there, and hopefully it's actually real so that we're not just talking crazy talk right now. So, what is that thing? Well, let's break it up into two parts. First, there's the orange part, which is h bar c partial mu theta. Set that aside for the moment. And we also have the purple part, which is psi bar gamma mu psi. Now, psi bar gamma mu psi is actually a very important quantity, and you see this quantity all the time when you're dealing with the Dirac equation. This is the probability forecurrent divided by the speed of light. And what that is a four-vector where the time-like part is the probability density, And by the way, here I'm using rho for probability density. Confusingly enough, later on it's going to mean charge density, but, in context it makes sense. Okay. Anyway, now J1, J2, and J3, that is the spatial parts of the probability forecurrent, are going to be the probability current, so the way that probability density flows from one place to the next. So this purple term has to do with how much of the electron is at some point in space and how much it's flowing. And this is a contravariant four-vector. Now, if you look at the orange term, you see the downstairs mu in the foregradient and a couple of constants, so that's going to be a covariant four-vector. And we know that because the Lagrangian density has units of energy density, this orange term is going to be some kind of covariant four-vector that's going to couple to the forecurrent in an energetic way. Which, by the way, that sounds a lot like the electromagnetic four potential. So the electromagnetic four potential is a four-vector where the time-like thing is voltage, or in SI units, V over C, and the spatial part is the magnetic vector potential. And that's the kind of thing that if you multiply it by the forecurrent, you're also going to get this energy associated with voltage acting on the probability density, and the vector potential acting in a momentum kind of way on the currents. So we're getting hints of the four potential in here. And that's good because that means that maybe we can ascribe a physical meaning to this. But I don't want to import any expectations or intuitions or assumptions about the electromagnetic four potential. For now, we're just going to regard this orange term as some kind of four vector, and we're not going to impose any constraints on it other than that it has to be real, and we're assuming that it's real and we're going to predict its properties and we're going to see if they map onto reality. Well, anyway, so starting with this really blank slate perspective of just saying, look, this is a covariant four vector, and so let's just call it A sub mu, like the most generic thing you can imagine calling a four vector, right? So that lets us write the orange and purple expression as A mu psi bar gamma mu psi. But actually, you know what? Here, we're going to do something here. So the way we've defined A mu, you'll notice that we don't have the freedom to change the units of A mu, because A mu is very directly defined in terms of h bar and c and the foregradient of a phase angle. So let's go ahead and do this. We'll define the four vector capital A mu, and it'll be the same as A mu, but we'll bring in a factor of -1 over q, where q is just some number, and right now we'll leave it undefined, but what that does is that doesn't lock us into a particular unit scale for A, right? Because we can always kind of redefine what we mean by q, and we can say now our base unit for A is going to be smaller or bigger or whatever it is, and we can adjust q accordingly. So we're building in a degree of freedom there without really changing anything in a meaningful way. But what about the minus sign? That is the Benjamin Franklin minus sign. This is purely conventional. In an ideal world, we wouldn't have to put it there, but you'll notice if we write out the orange and purple expression now in terms of capital A mu, we're going to have -q, capital A mu, psi bar gamma mu psi. And so when we bake into our definition of A mu this -1 over q, that ends up manifesting as a -q times A mu in the Lagrangian term. So at the end of the day, those cancel out. So that's fine, right? So whatever magnitude we put for q, that's going to cancel out by the definition of A mu, and that just gives us the freedom to scale the units of A mu to whatever we want them to be, which as we'll see later in the video, that's going to be helpful. But then the minus sign and the other minus sign cancel out, so we're not actually changing any physics by bringing in this minus sign here. Okay, so we're starting to massage this term in the Lagrangian into this covariant four vector times the contravariant four currents. We're starting to get hints of the electromagnetic four potential, and so this is kind of starting to be credible and kind of starting to make sense. But there is a problem here, and this is, if we want to believe that A actually exists, and that it's not just something we're making up in order to solve a problem and just making stuff up randomly, but if we want to say, no, there is actually this four vector field, it actually exists, and it actually couples energetically to psi, then we have to give A a life of its own. Because you'll notice that as it's defined here, A is directly dependent on the foregradient of theta. So if we don't apply a phase transformation, say theta is just 0, then A is 0. A goes away just because we didn't do a transformation. So the way we've defined it here, we have way too much control on the existential status of A, just based on whether or not we're actually messing around with theta. And so what we need to do instead is say, no, A is not defined in terms of the foregradient of theta. A is whatever A is, but it has the ability to be transformed by the addition of the foregradient of any arbitrary theta field. Okay, hold on now. So what have we done here? Well, we have a Dirac-Lagrangian that doesn't have local phase symmetry. We realized the only thing to do to give it local phase symmetry is to add a term that cancels out the mess. Then interpreting that term, we recognize that it corresponds to the existence of a four-vector field that couples energetically to psi. And in order for this to be credible, we have to let the four-vector field have a life of its own. But then one wonders, what kinds of energy are going to be contained in the independent life of the four-vector field A? Because if we're really saying that A exists, then we have to let it exist, and existence has consequences. And when A flops around, there's going to be some kind of energy in that, right? There has to be, otherwise A doesn't really have an existence on its own. And in order for any of this to be credible, we should hope to see at least one way that A can manifest energetically independent of its relationship to psi. Because if all A does, if A's only claim to existence is its interaction with psi, that's kind of dubious. I don't know if I trust that. But if A actually exists on its own in some way, then that lends a tremendous amount of credibility to this idea. And it gives us testable predictions of what does it look like when A manifests energetically, and how is A constrained, and what patterns are there, and what can we say about this, and what kind of theory grows out of the logical consequences of symmetry in the Dirac field and the corresponding freedom in A. It's like, okay, there's something we can now explore. We need to find a way that A can exist on its own, independent of its relationship with psi. Okay, so we're looking for ways that A can exist on its own, outside of its interaction with psi, and one of the most natural questions we can ask is, does A have mass? And the way to answer this question is to say, okay, well, if A had mass, how would that contribute to the Lagrangian? And is that allowed, or would that spoil the phase symmetry of the Dirac field? So one of the things that we've seen about A is that it has to be able to come in and clean up the Lagrangian, no matter how much we mess around with the phase field. When we multiply psi by an arbitrary phase field, and we're creating all these energy and momentum gradients and we're messing up the Lagrangian, our four-vector field A has to come in and offset that and clean that up. But meanwhile, we have to have total freedom to do whatever kind of phase field we want to do. So it follows that there can't be an energy cost or an energy benefit associated with how much or how little of A we have. We want to be able to pull in as much as we want. It's like, imagine you spill a gallon of milk on the floor and you would grab a whole bunch of paper towels to clean it up. Or maybe you just spill a couple drops of water on the floor and you grab one paper towel to clean it up. That's not a great analogy, but the point is, if A is going to be the best picker-upper of a mess that we're making in the Lagrangian, then we have to be able to pull in as much or as little as we want. And we can't meet any resistance that comes along with, well, you're pulling in too much A, or, well, you're not pulling in enough A. No. We need to be able to pull in as much as we want. And what this implies is that A has to be a massless four-vector field. Because if A had mass, then the amount of A you have changes the energy landscape, and so therefore it can't clean up the mess that we're making, because then A itself would actually violate the symmetry that its whole purpose is to come in and provide the Dirac equation. But similar reasoning would also seem to suggest that the derivatives of A can't contribute to the Lagrangian either. Because depending on how you mess with the phase field, sometimes you might need to bring in an A field to clean it up that's a little bit scrunched, or maybe not as scrunched, or is floppy or not so floppy. And so when you think about the space and time derivatives of A, if any of those contained any energy, that is, if the field were like kind of elastic, then it would seem like that would also violate the local phase symmetry of the Dirac field. Because in just the same way that we need to be able to pull in as much A as we need, or as little A as we need, we should also be able to pull in as scrunchy or as floppy of an A as we need, without there being any change in the Lagrangian. But if that's the case, then A really can't do anything on its own. Because if the amount of A can't contain energy, and if the derivatives of A can't contain energy, then A's only claim to existence would be the way that it augments the energy momentum landscape of psi. And that's not very satisfying. But fortunately, it's not very true either, because there is one secret loophole where you can set a derivative against another derivative. And so even though each of these terms is affected by arbitrary phase fields, the way in which they're affected is equal and opposite, and so it cancels out such that the whole expression is completely agnostic to, completely unaffected by, any arbitrary local phase transformation. So this loophole has a very particular form, a very specific form, and it has to be of the form partial mu a nu minus partial nu a mu, because then the changes are going to cancel out. Let's look at an example just so you can see specifically how this works. So consider partial 1 a2 minus partial 2 a1, or in other words, the derivative of the y component of a with respect to x minus the derivative of the x component of a with respect to y. Now, if we apply a phase transformation on psi, then a is also going to have to transform, so it's going to pick up that term of negative h bar c over q times the foregradient of theta. And so therefore, if you want to split that up into components, ax is going to pick up a term that has to do with the derivative of theta in x, and ay is going to pick up a term relating to the derivative of theta in y. So now if we evaluate this expression, partial x a prime y minus partial y a prime x, that is the derivative expression applied to the transformed a, we can evaluate both terms. One of them is going to be the x derivative of the transformed ay component, including that y derivative of theta term that gets picked up during the transformation. And the other term is going to be the y derivative of the ax component minus that x derivative of theta term. Now, based on the symmetry here, you can kind of see how these things are going to cancel out. But if you go ahead and evaluate this through, let's go ahead and separate out the derivatives of a from the derivatives of those theta terms, and we can see partial x ay minus partial y ax minus h bar c over q times this term that involves the x derivative of the y derivative of theta minus the y derivative of the x derivative of theta. And because the order doesn't matter when you're taking a second derivative, those terms are going to cancel each other out, and what we're left with is the partial x ay minus partial y ax, which is exactly the form of the expression applied to the unmodified a field. So in other words, no matter what theta field we put in, this expression involving partial x ay minus partial y ax is going to end up being totally the same because each half is going to be affected by an equal and opposite amount. And this generalizes to all possibilities for mu and nu. And so in general, the expression partial mu a nu minus partial nu a mu is going to be completely insensitive to any arbitrary local phase transformation. So this is like a special trick that allows a to escape the tyranny of the phase field. And notice that the form of the trick, the contour of the trick, fits like a key in a lock to the constraints of local phase symmetry. The reason that this loophole, the reason that this trick has the form of a derivative minus a derivative, is that the way the phase field affects a takes the form of a derivative. And so the nature of this trick follows necessarily from the nature of local phase symmetry in the Dirac field. Now, naturally, the question arises, how many different ways are there of applying this trick? And so therefore, how many different ways can we expect a to flop around on its own, independently of its relationship with psi? Well, in our universe, there are 3 dimensions of space and 1 dimension of time, for a total of 4 dimensions of spacetime. And if you think about the different combinations of things, there's actually 6 ways to pick 2 of those dimensions. See, because there's 3 ways to pick time and a space dimension. You could do t and x, you could do t and y, you could do t and z. And also, there are 3 ways to pick a space and a space dimension, because each of those ways is going to leave 1 dimension unselected. So for example, you can do not x, not y, and not z. So in other words, yz and xz and xy. Okay, and for each one of these ways, we can write the expression which corresponds to the derivative of this component of a with respect to that component of spacetime, minus the derivative of that component of a with respect to this component of spacetime. And what each one of these things is actually going to be a scalar field at every point in space and time. Because A is a 4-vector that's defined throughout spacetime, and so this combination of its derivatives of its components is going to manifest as 6 scalar fields that can actually contain energy, like real energy, like for real actual energy. So this is quite an interesting situation. If we're taking this gauge theory stuff seriously, if we're really thinking that there must be this 4 vector and it must be able to flop around, and there's 6 ways for it to do that without being affected by arbitrary phase transformations, then we should expect to find 6 scalar fields pervading space and time which can contain energy. Now, how are we supposed to think about 6 scalar fields? I mean, that's kind of a good number of scalar fields. Well, if you look at the patterns that I'm showing here, you can see that we have 3 ways to pick a time and a space, and there's 3 ways to pick a space and a space. But first, let's look at the options that involve a time and a space. So those 3 options, those 3 scalar fields, are all basically the same thing. The only thing is one of them has to do with x, and one of them has to do with y, and one of them has to do with z. And so naturally, we can compile those 3 scalar fields into a 3-dimensional vector field. Because the one involving x, that's just going to be the x component, and the one involving y is just going to be the y component, and the one involving z is just going to be the z component. And this vector field is what people have been calling the electric field. So now it's a profound and subtle point that I want to make here. I'm not saying import your intuitions and assumptions about the electric field. I'm saying that these 3 scalars that involve a time and a space, by virtue of their common origin and by virtue of the nature of their definitions with regards to the derivatives of A, these 3 scalars can naturally be compiled into a vector, and that vector has exactly the properties of the electric field. And so this field that people have been calling the electric field from the Greek word for amber, it doesn't really have anything to do with amber, right? So you can forget about the biases that come in when you think about the word electric. No, it's just a straight up vector field that comes out of the math. So I'm going to call it the electric field, and I'm going to prove to you that it is the electric field as we derive Maxwell's equations. But notice that, earlier I mentioned that it feels like electromagnetism is an expansion pack that you have to put on your worldview, because you have to take it on faith that things like the electric field and the magnetic field exist. But you don't have to do that anymore. You don't have to believe as a first principle that there is such a thing as an electric field. You just have to believe that the Dirac field has local phase symmetry, and then you get the electric field automatically for free by virtue of 3 of the 6 ways that A can flop around on its own. So, you probably see where this is going. What about those other 3 ways? The ones involving space and space? Well, here it's less obvious how to make a vector out of these. And in fact, you can't. But you can make a pseudovector. And a pseudovector is a thing that looks like a vector, but secretly it's not. Because when you look at its reflection in a mirror, it picks up a minus sign that a vector wouldn't pick up. So for example, if you imagine an angular momentum vector, it's actually a pseudovector, because it's based on the way things are swirling around. And if you reflect that, it's going to swirl the other way, so the vector is going to flip. And so every pseudovector is secretly an oriented plane. Well, anyway, so let's call the pseudovector B for pseudovector. And the x component of B is going to be the way that doesn't include x. So the one that includes y and z. And it's actually going to be the negative of that way. And the negative sign is there so that we can compile these ways into the curl of the spatial part of A, as we'll see in a moment. But it's okay to put a minus sign on this because the minus sign doesn't actually give us a different degree of freedom. It's still the same thing, right? It's still the same mode that A can flop around in. Okay, so then for the y component of B, for that one, we're just going to take the second option involving x and z. We're not going to put a minus sign. And then for the z component of B, we're going to take the minus sign of that third option that includes x and y. And that, if you compile into a vector and you recognize the definition of the curl, you'll see that this vector-like thing is the curl of the spatial part of A. That is the curl of the magnetic vector potential. And that is none other than the magnetic field. Okay, wait a minute now, hold up. This is really an astonishing thing to say, that the electric and magnetic fields are just ways of mathematically encapsulating the 6 ways that A can flop around on its own. Like, whoa. Like, I remember the first time I saw this, I was like, dizzy. Like, I had to sit down in a chair and take a moment to reflect and be like, wait a minute, what? Like, that's all the electric and magnetic fields are? Like, it's math? It's all pure math. Like, whoa. And, once you see this, you realize that you don't really even have to talk in terms of electric and magnetic fields if you don't want to. Because E and B, these things are, I don't want to say it's a useful fiction, because I think that's not quite accurate, but it's sort of an arbitrary convention. And if you've studied electromagnetism, you may have heard of the Faraday tensor. That's the tensor whose components are the components of the electric and magnetic fields. And that's sort of a more uniform, more holistic way of describing the situation with the 6 ways that A can flop around. But even the Faraday tensor itself, which we'll talk about in a moment, but even that tensor itself is just one way of describing what's going on. So the core concept here is don't take the electric and magnetic fields too literally. Don't even take the Faraday tensor too literally. Okay, well, maybe take that one a little bit more literally, but the point is, examine the root of these concepts, and you'll find that all it is just the 6 degrees of freedom that A has available to it without disrupting the local phase symmetry of the Dirac field. Now, I'm going to share with you a mnemonic device that has been stuck in my head, and for better or worse, because it's really effective and it's really memorable, but it's also kind of silly and whimsical. Which, now that I think about it, this is just a good thing. Okay, so here's the thing. In order to put in your mind a permanent understanding of the connection between the electromagnetic 4 potential and the electric and magnetic fields and/or the Faraday tensor, what you can do is, in your mind, create a category called the 6 ways, and regard this category with a kind of mystical significance. So imagine there's some meditation music playing, maybe a little bit of pan flute, and in your mind, think about, oh yes, okay, we have this 4 potential, and then there are the 6 ways that it can flop around on its own. And when you think about this in your mind, pretend that it's kind of a spiritual fact, like some spiritual knowledge that you've gained access to, that you've tapped into, like now you can see the 6 ways that A can flop around. And remember that, because I know it's silly, I know it's like there's no logical reason to think about it in that way, but the point is, if you keep that in mind and remember that it's just 6 ways that A can flop around, then you'll always remember what the electric and magnetic fields are, and you'll always remember what the Faraday tensor is. And in general, you'll feel a lot more comfortable with all of this math. And you'll also be able to go kind of like underneath the electric and magnetic fields, where you don't take them so literally and you can kind of see where they come from. And this will give you some real, genuine insight. So for example, let's use this perspective about the 6 ways to derive the homogeneous Maxwell's equations. We're going to start off with Gauss's law for magnetism, and this law states that the divergence of the magnetic field is 0, which implies that every magnet has a north pole and a south pole. So to do this derivation, all we have to remember is that B, the magnetic field, is the pseudo-vector part of the 6 ways. And in particular, B is the curl of the spatial part of A. Now, if we want to calculate the divergence of B, all we have to do is calculate the divergence of the curl of the spatial part of A, right? Of that vector potential. And here, if you've learned vector calculus, then you'll know what this is right away. The divergence of the curl is 0. And this is a general mathematical statement. And so there in one line, there's the proof, right? So the divergence of B is the divergence of the curl of the spatial part of A, and so therefore the divergence of B is 0. That's literally the proof of Gauss's law. It comes right directly out of the nature of the equations. It's beautiful. Okay, this proof was so short that let me actually go ahead and just give a quick proof that the divergence of the curl is always 0. For those of you who haven't seen that before, this might be helpful. And it also kind of shows like what's going on here in a little bit more detail. So if you take the divergence of the curl of any vector field A, then you can write that out by putting in the definition of the curl, which is this expression that has a bunch of partial derivatives minus other partial derivatives. And to take the divergence of that, you just go ahead and take the derivative of each component along that dimension, and then you just add that all up. So that's the divergence operator. And when you do that and we factor things out, you get a bunch of second derivatives, and then you'll see that they actually pair up and cancel each other out. And so anyway, you end up with 0. So that's a really general mathematical statement. And that is why Gauss's law is a thing. At the end of the day, it comes down to the fact that the B field, that pseudo-vector field, is the curl of another vector field. So yeah, no, it can't diverge, it can't converge. It's just zero divergence. Oh, and by the way, you'll often see Gauss's law written in two different ways. There's the differential form, but then there's also the integral form. So the differential form is what we just derived. That's the idea that the divergence of B is 0. But that can also be written in a more macroscopic way using the integral form, where we can express the same fact in terms of a flux integral of B through any closed surface. These two things are directly related by the divergence theorem, which tells us that the volume integral of the divergence of a vector field is equal to the flux integral of the closed surface containing that volume. The divergence theorem basically just tells us that one way to think about what the divergence is as like a flux integral volume density. Or vice versa, one way to think about what a flux integral is like the accumulation of sources and sinks within a closed surface. So if you take the divergence theorem and you plug in the fact that the divergence of B is 0, then you can prove that the flux integral of B through any closed surface is also 0. Both ways of saying this are conveying the same basic idea, which is that magnetic fields, they don't source and they don't sink, they don't poke more out than they poke in. They just kind of swirl around. Okay, so that's 1 Maxwell's equations down, 3 to go. Next up, we'll do Faraday's law of induction. And this tells us that the curl of the electric field is -1 over the speed of light times the time derivative of the magnetic field. In other words, the way the electric field is swirling around in space has to do with the way the magnetic field is changing in time. So the proof of this fact is very similar to the proof of Gauss's law for magnetism. All we have to do is write the definitions of E and B in terms of the components of A, because, as we saw earlier, E and B both come from the 6 ways. And so when we write that out, we get that E is -1 over C partial A partial T minus the gradient of the time component of A, which, by the way, here I'm writing as A sub T. It's kind of a non-standard notation. Normally at this point you'd write it as V in Gaussian units or V over C in SI units, because that's voltage, right? So the time component of the 4 potential is voltage. But I'm writing it here as A sub T because I want to emphasize the unity of all these equations. I know when I was learning this stuff, I would see A and V, and they kind of felt like different things. So, I don't want to split that out unnecessarily, although, of course, it is voltage, so. Well, anyway, and now looking at B, again, it's just the curl of the spatial part of A, so the curl of the vector potential. Okay, cool. So let's just go ahead and calculate the curl of E and see if it equals -1 over C partial B partial T. And if it does, great. That's the proof of Faraday's law of induction. So let's do it. Okay, so to calculate the curl of E, we're going to take the curl of the definition of E, which is -1 over C partial A partial T, minus the gradient of the time component of A. And the curl is a linear operator, so we can go ahead and break up that expression. We can take the curl of both parts, and so that gives us -1 over C times the curl of the time derivative of the vector potential, minus the curl of the gradient of the time component of A. Well, earlier we saw that the divergence of the curl of a vector field is 0, and similarly, the curl of the gradient of a scalar field is 0. And so that term, negative curl of the gradient of A sub T, that just goes away, that's 0. By the way, the proof for that you can imagine by, if you've ever seen that drawing of the stairs, where it's like 4 stairs and it goes up in a spiral, and somehow it's like it's always spiraling upstairs. That's not real. That can't happen in real life because the slope of something doesn't curl, right? So the curl of the gradient is 0. You can prove that in a more formal way if you want, of course, using the definitions of curl and gradient. Well, anyway, so that term goes away, and we're left with -1 over C times the time derivative of the curl of the vector potential, that is the spatial part of A. And, well, wait a minute. the curl of the vector potential, that's the definition of B, and so that expression is -1/c times the time derivative of B. So yeah, that's totally true. And so we've just proven Faraday's law of induction. So to convert Faraday's law of induction from the differential form to the integral form, typically what you want to do is take the flux integral of both sides of the equation through some surface. And this is usually imagined as a circle, just to keep things simple, but it doesn't actually have to be a circle. Okay, and now all we have to do is apply Stokes' theorem to the left-hand side of the equation. So Stokes' theorem is the idea that the flux integral of the curl of a vector field through some surface is going to be equal to the circulation integral of that vector field dotted with the line element around the surface. And one way to think about what Stokes' theorem is if you're like, okay, what is the flux of the curl of a vector field through a surface? That's just how swirly the vector field is around the edge of that surface. Anyway, what that lets us do is that lets us write the left-hand side of the equation in terms of a circulation integral or a line integral instead of a flux integral, and that is Faraday's law of induction written in integral form. And this is the form of Faraday's law of induction that you'll typically see when you have those experiments where you're like poking a magnet through a solenoid, you know? And it's like, hey, the rate of change of magnetic flux is inducing a swirly electric field in the solenoid, and so you can make electricity just by moving a magnet, and wow, isn't that amazing? But now that we're hip to the 6 ways, we know that it's actually not too surprising that this is the case. Okay, well that is the homogeneous Maxwell's equations. They are baked into the nature of the electric and magnetic fields. And in a moment, we're going to see how to calculate the inhomogeneous Maxwell's equations. These ones also have to do with the nature of the electric and magnetic fields, but they also include electric charge and electric currents. And so if we want to derive the inhomogeneous Maxwell's equations, we're going to have to take that into account as well, and we're going to have to look not just at the nature of the electric and magnetic fields, but also the details of how they couple to the electron field and all of that. So anyway, we'll get to that in just a moment. But before moving on from the homogeneous Maxwell's equations, I want to make a point about the philosophical status of these equations. So imagine that I came up to you and I said, hey, I've made a discovery. I've noticed that whenever you add the magnetic field to itself, the result is the same as doubling the strength of the magnetic field. So B plus B equals 2B. So wow, isn't that amazing, you know? Hey, maybe this can be a fifth Maxwell's equation. Let's call it B. Hill's law of magnetic addition. So can I get a Nobel Prize? I mean, isn't this an amazing discovery? It's like, no, it's not at all, not even remotely. But why? I mean, is it not true? Well, no, it is true. So the question isn't to be or not to be, but rather, should the mind suffer the slings and arrows of outrageous and irrelevant equations? And of course the answer is no. If an equation is obvious, it's unnecessary, and it doesn't have to be a thing. And from a gauge-theoretic perspective, the same is true when it comes to the homogeneous Maxwell's equations. When you think about A and the ways that it can flop around energetically, you realize that there's going to be a vector, there's going to be a pseudovector if you want to talk about it in that language. And if so, then the pseudovector is going to be the curl of the spatial part of A, and curls don't diverge. So we don't really need to say that it doesn't diverge, it just doesn't diverge, right? Based on the definition, based on the nature of how it is. So Gauss's law for magnetism is sort of like B plus B equals 2B. It's like, well, yeah, okay, but, you know, we don't necessarily need to even say it anymore. And the same is true of Faraday's law of induction. That just comes straight out of the common definition of the electric and magnetic fields. So it's actually really neat because when you think about things from a gauge theory perspective, you realize that when you understand the homogeneous Maxwell's equations, they disappear, they vanish. Philosophically, they vanish. They're still useful. Look, from an engineering perspective, if you're writing software, you'll still use these equations. I mean, they're fine, they're true. But philosophically, you don't need to rely on these anymore. They don't hold anything up. They're just manifestly true, insofar as the Dirac field has local U1 phase symmetry. On the other hand, we also have the inhomogeneous Maxwell's equations. And these equations involve charge and current, and while they also are a logical consequence of local phase symmetry, they're a bit harder to derive. Actually, they're quite frankly a lot harder to derive, because in order to derive it, we have to think not just about the nature of the electric and magnetic fields, but we have to think holistically about the interaction between psi and A, and derivatives, and space and time, and a lot of different things. So in a few moments, we're about to bust out the variational calculus, and we'll actually derive those equations. But first, in order to do that, we have to introduce a couple of concepts. So first, we're going to talk about the Faraday tensor, and then we're going to use the Faraday tensor to write the Lagrangian of quantum electrodynamics. Okay, so we saw earlier in the video that there are 6 ways that A can manifest energetically independent of local phase transformations on psi. And we saw that if you arrange them so that the time and space options are on one side, and the space and space options are on the other side, then you see the electric field and the magnetic field. But there's no law of physics that says that we have to arrange our thoughts in that way. The only thing we're really constrained by fundamentally is the fact that there are 4 dimensions of space and time. So suppose we want to have some equations that are more unified and more conceptually elegant than equations involving electric and magnetic fields. Like, let's say we want an equation where maybe it leverages matrix algebra, maybe it's something that lends itself better to computation and is a little bit more structured and organized. Well, one way to go about that is to say, okay, well, we can make a table where each row in each column is going to correspond to one of the 4 dimensions of spacetime, and then we can populate the table with each option of picking those 2 dimensions and applying the loophole that lets A flop around energetically, independent of local phase transformations. So this table goes by the name of F mu nu, and this is called the Faraday tensor, also known as the field strength tensor. This is an object whose components are components of the electric and magnetic fields, but the tensor is not inherently fractured in the same kind of way that equations involving electricity and magnetism are going to be fractured. Now, when we look at this table, it's quite a mess. I mean, there's a whole bunch of characters and a whole bunch of different options, but there's a couple of things we should notice. First of all, each one of these options has the same form. So each element in F mu nu is just partial mu A nu minus partial mu A mu. And so even though it's a lot of things, it's all the same kind of thing. But now the thing is, wait a minute, is this 16 ways? 4 by 4, that's 16? I thought there were only supposed to be 6 ways. So something's wrong here, right? But don't worry, the situation is not as dire as it seems, because if you focus on the diagonal terms, you can see that each one of these diagonals is just a thing minus itself. And so those are all 0. So what we have here is a tensor whose diagonal is 0, and then it has an upper triangle and a lower triangle. Okay, so there's not actually 16 ways. Well, wait a minute. There's still 12 ways. And that's twice as many ways. There should not be 12 ways. There should be 6 ways. But now notice the symmetry of this tensor. So for example, look at the blue term that I've highlighted here, and compare it to the red term. Well, if you multiply the blue expression by -1, and then switch its components around, you're going to end up with the red expression. So in other words, those 2 elements are the same thing up to a minus sign. And so actually, collectively, they comprise only a single degree of freedom, only a single way, not actually 2 different ways. And if you pick another pair, you can see that it's the same thing. So for example, the ones involving 0s and 3s, each term is actually the negative of its diagonal counterpart. And if you apply this to the whole tensor, you can see that the top triangle and the bottom triangle are like mirror images of each other, but with a minus sign. And that's okay. Like if you look in the mirror, technically you're backwards, but it's still just you. There's nothing like you look in the mirror and it's like someone else in there. So if you think about the degrees of freedom, you can see that actually, yeah, there's only 6 ways. Well, now if that's the case, then we should expect in each of these triangles to find the components of both the electric and the magnetic fields. So first, if we start with the components in the time row and the space columns, we can see that these are the definitions of the components of the electric fields that we identified earlier. Now, because the tensor is mirror reflected with the minus sign, and by the way, this is called anti-symmetry, so that we can say that the matrix is anti-symmetric, then the time column and the spatial rows are just going to be the negative components of the electric field. Okay, and now if we look at the space and space components in the top triangle, what we see here is just the components of the magnetic field that we identified earlier. There's some differences in minus signs because of the way the cross product is in the definition of the magnetic field. My advice, honestly, don't worry about minus signs in any of this. Okay, I mean, be careful about it, but like, don't try to memorize them all. There's just so many minus signs. I don't know about you, but personally, the hardest thing about physics is knowing where to put the minus sign and knowing where to put the factor of 2. So the philosophically important thing is just to see that the Faraday tensor contains the electric and magnetic fields, and don't worry too much about minus signs. Especially when you factor in like index lowering and index raising, and it's like, it's okay if you drop a minus sign when you're learning this stuff. That happens, that's natural. I still do it to this day. So, okay, and once again, if we look at the bottom triangle, we see a reflection of the same thing, so down there we also have the magnetic field components. Now when you look at this square, you see it's actually quite redundant, and you don't really need to imagine it as a square. You can just focus on one of the triangles, whichever one you prefer, that's fine. And in your mind, you can imagine it that there is an electric field rho, and then there's like this little magnetic triangle. One thing I should say is I know this seems a bit unnecessary. I mean, we have a 4x4 matrix with 16 possible terms, and we're only caring about 6 of them. That's only like 40% real estate utilization, so it seems not ideal. And in a way it isn't. I mean, there are advantages of using electric and magnetic fields in that it's kind of cleaner in some sense. But notice the conceptual simplicity of having all of these degrees of freedom in one object. And think about the computational benefits that come along with that, with being able to write it as an array. And then think from like a Zen perspective that anything that has computational benefits is also going to be kind of more elegant and maybe more in line with a more concise and meaningful description of nature. So this Faraday tensor is actually a really cool thing. And as we'll see later in the video, this is going to let us write the equations of electromagnetism in a much more elegant way. Oh yeah, and also one more thing is when you think about this, it's like, okay, you can do electromagnetism, any calculation, without using the electric and magnetic fields. So when you embrace the Faraday tensor, you see that even the word electromagnetism is almost like an antiquated portmanteau. You might as well call it Faradayism or something. Or light, or I don't know, local phase symmetry, whatever you want to call it. Well, anyway, while we're here, I should also tell you about the upstairs Faraday tensor. So first of all, if you notice that the mu nu on this matrix is downstairs, you can also have an upstairs version, and that you get just by raising the indices, and all that means, and by the way, this depends on the metric you're using. Here again, we're using mostly minus. But when you take it upstairs, the electric field components pick up a minus sign. And again, don't worry too much about that. There's like minus signs and not minus signs everywhere, and it's confusing, but that's okay. This is similar to having like a contravariant or a covariant 4 vector, and you're going to multiply them together. And, so this kind of goes to the structure of special relativity, but we're going to kind of see how this appears in equations later on. So don't stress too much about trying to memorize where the minus signs go. It's all good. And also, you can always refer to Griffiths' equation 7.71 to see the definition of the upstairs Faraday tensor. Okay, so now that we've seen the tensor f mu nu, let me tell you about the scalar quantity f mu nu. And what this is like the magnitude squared of the Faraday tensor. And this is a very important ingredient in the Lagrangian of quantum electrodynamics. So to understand what this is, the first thing we have to do is recognize that we're using the Einstein summation convention, and because mu and nu are both repeated, they're both summed over, and so this is actually going to be a sum over 16 terms, one for each possibility of mu and nu. And what each one of these terms is the product of a downstairs Faraday tensor element times the corresponding upstairs Faraday tensor element. We have to be mindful of the downstairs and the upstairs and the signs, but that's all good. You don't actually have to do this calculation like more than once, so I just want to do this real quick and I'll show you what it equals, and then you can just remember what it equals. Okay, so first of all, if you look at the terms where mu equals nu, and you think about the zero diagonal in the Faraday tensor, you can recognize right away that all of those terms are going to be zero. So those are not going to contribute to the sum. And now if we look at the terms where one of the indices is 0, we can substitute in the definition of the components of the Faraday tensors, and we can see that these are all just going to be the electric field components times themselves with a minus sign. And so that just becomes negative components of the electric field squared. And if you want, you can add those all up as just the negative magnitude squared of the electric field. And similarly, if we look at the terms where neither of the indices are 0, we see the components of the magnetic field, And in this case, they either have two minus signs or no minus signs, and so those all end up being positive. And so you end up with the positive squares of the magnetic field components. Now, to add this all up, we just have to draw a diagonal line and recognize that the top and bottom halves are the same thing. And so this expression, when you add it all up, it ends up being just 2 times the magnetic field magnitude squared minus the electric field magnitude squared. So remember this, whenever you see F mu nu, if you want to think about that in terms of electric and magnetic fields, all that is twice the magnetic field squared minus the electric field squared. And this is a special quantity because you know how magnetic fields arise from moving charges? So let's say if I'm electrically charged and I'm just sitting here and we're sitting together on the couch or whatever, then I'm putting off an electric field, but I'm not putting off a magnetic field. But if you're walking by, then now all of a sudden, relative to you, I'm a moving charge. And so now just by walking by, you sense a magnetic field in the room. Admittedly, a very weak one, unless you're walking by very quickly. But anyway, all that's to say is that the electric fields and the magnetic fields on their own are not Lorentz invariant quantities. Different inertial observers are going to disagree on how strong the electric and magnetic field is at any particular point in spacetime. But all inertial observers are going to agree on this quantity, that is the difference in the field strength squared. This is similar to the invariance of the spacetime interval or any other Lorentz invariant quantity. Now, conventionally, this F mu nu term, you often see it divided by 16 pi in Gaussian units. And so on the right side, that just ends up being 1 over 8 pi times the magnitude of the magnetic field squared minus the electric field squared. And what each of those expressions is, think of it as the energy density of the magnetic field minus the energy density of the electric field. And you know what, now that I'm looking at this, we've got the b squared minus the e squared, but we're using the mostly minus metric, and so we kind of want something where the time-like thing is positive and the space-like thing is negative. So let's actually multiply through by a minus sign. And this is basically just the same thing as before, but now the time-like thing has a positive sign and the space-like thing has a negative sign, which kind of aligns more nicely with the whole mostly minus thing, you know? So a quantity like this is just asking to be popped into a Lagrangian. And in fact it is. So this is the photon's kinetic contribution to the Lagrangian of quantum electrodynamics. Now when you first see this, you're going to think, wait a minute, 1 over 16 pi, where does that come from? And the answer is, that's put there in order to make the equations pretty. And the reason we can do that is because remember earlier, we said that we're going to make the charge this letter Q. Instead of just the number 1, we're going to say, let's make this Q, because then we have the flexibility to define the scale of A. Well, now we're cashing in on that. And we're going to say, okay, we're going to define the scale of A such that the coefficient on this part of the Lagrangian can be a nice clean 1 over 16 pi. So this is an acceptable, legitimate move. But it is a little bit unsatisfying that we have this degree of freedom here and that we get to make this choice in the first place. In an ideal world, it'd be nice if the scale of the photon's kinetic contribution were locked in by some kind of deeper principle. And that's the problem of the fine structure constant, so we'll talk about that more in a moment. But first, I want to write out the Lagrangian of quantum electrodynamics, so we can see how everything fits together. First up, we have this term psi bar, I h bar c gamma mu partial mu minus mc squared psi, and that is the free Dirac term, that's the electron's kinetic and mass energy. Then we also have the interaction energy, which is negative q psi bar gamma mu psi times a mu, and you can think of that as the electron's forecurrent coupled to the forepotential. So that is the energy associated with the interaction between the electron field and the photon field. And then finally, we have the kinetic energy of the photon field, which, as we've just seen, is this quantity 1 over 16 pi F mu nu. And one thing that I haven't really done is I haven't really justified why it is that the kinetic energy of the photon field should have the form that it does. I mean, as we've seen, we can arbitrarily choose what we want that constant to be, so that's okay. And also, if we're thinking about it relativistically, we do need a Lorentz invariant quantity, and F mu nu is the Lorentz invariant quantity, the simplest one, that we can make out of the Faraday tensor. And we have to use the Faraday tensor because that encapsulates all of the degrees of freedom by which A can flop around independently of a local phase transformation. And so if we tried to use anything outside of the Faraday tensor, we're going to spoil the phase symmetry. So the form of this component of the Lagrangian is very, very plausible. It's kind of like the simplest thing it could be. But the question arises, well, why couldn't it be that squared or that cubed, or some expression involving higher orders of this term? Well, there's a couple things I want to say about that. And oh, by the way, shout out to Jonathan Gorard for helping me figure this out and think this through. Follow him on Twitter. That guy's like a super genius. So first of all, if the term f mu nu were more complicated with higher powers and that sort of thing, then we wouldn't be able to derive the inhomogeneous Maxwell's equations. And we'll see that in a moment. Part of the derivation is going to be involving taking derivatives of the Faraday tensor, and you'll see when that time comes that it's a good thing that it's f mu nu and not something else. So to the extent that we want these ideas to be coherent with Maxwell's equations, we need this term f mu nu, because otherwise we would end up with nonlinear equations, and Maxwell's equations are famously linear, so... Okay, but technically that kind of feels like we're cheating, because it's like we know we want to get Maxwell's equations, we know they're linear, and so therefore we're kind of preempting that, and so we're making sure that f mu nu is simple. And that's actually a good point. So let me just confess that right now we're leaning a little bit on Occam's razor, and we're just saying, look, this is the simplest Lorentz invariant scalar that we can make out of the Faraday tensor, and so in some sense, this is mathematically the most plausible form of the Lagrangian that we can come up with. Then we're going to realize that it leads to electromagnetism, and so we're going to sort of take this as true. But strictly speaking, just the constraints of local phase symmetry and special relativity on their own do not necessarily imply that this part of the Lagrangian has to have precisely this term. But anyway, it just so happens that in the universe in which we find ourselves, and at the kind of energy scales that we're typically interested in, electromagnetism takes the form of linear differential equations, and that's precisely what we get when this term in the Lagrangian has the simplest form that it can have. So, okay. Oh, and remember, technically this expression with the fancy L, it's actually the Lagrangian density. Everyone calls it the Lagrangian, but it's the Lagrangian density. So if you integrate this over space, then you get the Lagrangian, and if you integrate it over spacetime, you get the action. And then the principle of least action lets you turn the Lagrangian into the governing equations of whatever system you're looking at. So that's kind of how this plugs into physics. Okay, so let's reflect on this for a moment. What we have here, this equation, this iconic, beautiful equation, is the QED Lagrangian. And this is the seed that grows into the electromagnetic phenomena. So the blossoming of this equation is responsible for like most of the worlds that we see around us. It's an amazing thing. And you can think of it as the Dirac Lagrangian with the local U1 symmetry upgrade. So if you take the Dirac Lagrangian for a free electron and say, I want to do whatever minimal thing I have to do to give that local phase symmetry, then this is what you end up getting. And so fundamentally, that's all this really is. So now let's go ahead and use this Lagrangian to calculate the inhomogeneous Maxwell's equations. And we do that by minimizing the action, which is the integral of the Lagrangian density over spacetime, with some arbitrary psi, so some arbitrary electron field psi, and we allow the photon field and its derivatives to vary and flop around as needed to relax the Lagrangian. Okay, so before we get into the calculation for the inhomogeneous Maxwell's equations, I want to draw an analogy to a famous problem in variational calculus that can serve as a kind of imaginative metaphor for the calculation that we're about to do. So this is the catenary curve problem, and the problem is, how do you calculate the shape that a telephone wire takes on between two telephone poles? And the key to solving this problem is to say that it's going to be the shape that minimizes the gravitational potential energy, because that's going to be the most relaxed shape. And you also have to put in your boundary conditions, so you say, okay, it'll be connected to this pole here and that pole over there, and it's going to have some constant length. And so given all the curves that have those constraints, which one minimizes the gravitational potential energy? And then the key insight at the core of variational calculus is to recognize that the optimal curve is going to be the one where if you give it some arbitrary infinitesimal nudge in any way that it can be nudged, then to first order, you're going to get zero response in the variable that you're trying to minimize. So in this case, if we took the telephone wire and we imagined giving it a little tiny nudge up and down here and there, the variation that we'd find in the gravitational potential energy for the optimal curve is going to be zero. And that's a special property of the equilibrium solution. And this is roughly analogous to doing an optimization problem in calculus where you can look for the optimal points by looking where the derivative is zero. When you're doing variational calculus, you can look for the optimal curve or surface or whatever by looking at the point where the variation in the variable that you're trying to minimize is zero relative to small infinitesimal nudges in every which way that the thing can be nudged. Of course, the nudges have to respect the boundary conditions of the problem. So, for example, in the case of the telephone wire, you see that the wires are connected to the poles, and the nudges don't change where they're connected. They only change in between the boundaries. That'll be relevant later, as we'll see. And so anyway, to solve the problem, what you end up doing is you calculate the gravitational potential energy as an integral over the curve subject to some constraints, and then you analyze that while adding to the curve some arbitrary nudge profile, some arbitrary function of x that vanishes to zero at the boundaries. And you'll find that the only way to ensure that is zero, that is the only way to ensure that the curve minimizes the gravitational potential energy, is going to be to satisfy some constraint in the integrand that ends up giving you a differential equation that you can then solve for the optimal shape of the curve of the telephone wire. And it ends up being a fairly tedious differential equation, but at the end of the day, you find that it is a cosine, hyperbolic cosine. And anyway, so that's kind of a lot of work just to be able to say, technically it's not a parabola, but that is what it is. And so the reason I bring that up is because the calculation for the inhomogeneous Maxwell's equations is actually very, very similar in essence to the calculation for the curve taken on by a telephone wire between two poles. Now, instead of a telephone wire, it's going to be the photon field and its derivatives that are allowed to vary. The condition is going to be that we're going to have some arbitrary electron field psi that A is going to couple to. And instead of minimizing the gravitational potential energy, we're going to be minimizing the action S as defined by the Lagrangian of quantum electrodynamics. And instead of working in a two-dimensional space, we're going to be working in a four-dimensional relativistic spacetime. But other than that, it's a very similar problem. So the reason I bring up this telephone pole analogy is to show you that even though what we're about to do is quite a calculation, in your mind you can have an image of the photon field relaxing around psi. And the constraint that makes this happen, the thing that A has to be like in order for that to be the case, is ultimately going to be an equation that describes how A has to be given some electron field psi. And when you talk about that in the language of charge and currents, we're going to find that that is indeed the inhomogeneous Maxwell's equations. This calculation is not for the faint of heart. We must approach it with courage and determination. We start with the principle of least action. First, we recognize that the action S is defined as the integral of the Lagrangian density over some chunk of spacetime. Then, applying the principle of least action, we're going to minimize this quantity. This occurs when the first variation in the action is zero. Sort of like optimizing by setting the derivative equal to zero. The action is minimized when any arbitrary infinitesimal nudge on the photon field has a vanishingly small effect on the action. So now suppose we have some arbitrary electron field psi. We want to know then what must be true of the photon field A, which is coupled to psi, in order to relax the action S into its minimum value out of all possible field configurations. What must be true about A in order for the principle of least action to be satisfied? Well, we can write out the variation in S as the variation in the integral of the Lagrangian density over spacetime, because that's the definition of S. And that's all fine and good, but now we want to know what happens when we give our photon field a little bit of a nudge. And we can nudge it not only in the value, but also in the derivatives of the field. Because, as we've seen, the photon field contributes to the Lagrangian in two ways. One, its value, its magnitude, at a particular point in space is going to contribute to an interaction term with the electron, so we for sure have to vary it with respect to its magnitude. But also, we notice that derivatives of A appear in the Faraday tensor, that is, in the photon's kinetic contribution to the Lagrangian. And so we're also going to have to vary the Lagrangian with respect to derivatives of the four potential. So the question is, how much does the action vary when we nudge the photon field and we nudge its derivatives? And the answer is, it's going to be the partial derivative of the Lagrangian with respect to each of those things that we're nudging. You can think of the partial derivative terms as a kind of sensitivity. And it's almost tautological, right? The amount to which the Lagrangian is going to be sensitive to a nudge in some variable is going to be the partial derivative of the Lagrangian with respect to that variable. So now what we have here is an expression involving partial derivatives of the Lagrangian with respect to A, as well as with respect to derivatives in A. Here I should make a point to note that mu as well as nu can each take on a value between 0 and 3, 0, 1, 2, 3. And so in this expression, we actually have 20 terms. I know it looks like 2 terms, but that first term involving nudges in A, that's actually 4 terms, one for when nu is 0, and then 1, and then 2, and then 3. And the second term involving the derivatives of A is actually 16 terms, one for each of the possibilities of mu and nu being 0, 1, 2, and 3. And that corresponds to the derivatives of each component of A along each dimension of spacetime. So in the integrand, we actually have 20 terms, but thanks to the convenient notation that we're using, we only have to write 2 terms that correspond to the general category of terms that are in this equation, and so we can carry them all through systematically without having to always write down each and every one. All right, so now the next thing we'll want to do is write the variation in the derivative of A as the derivative of the variation in A. Because if we can write that second term in terms of variations in A, that is nudges in the photon field, then we can factor out the nudges in the photon field, and we can bring together both of these terms. So because the variation and the derivative are independent, we can go ahead and write the variation of the derivative as the derivative of the variation. Now we're getting somewhere because you can see that the variations in the integrand are on the 4-vector themselves. We're no longer taking the variation of the derivative. But on the right-hand side, we do have the derivative of the variation. And as long as we have the derivative of the variation, we can't factor out the variation. So we need to do an integration by parts. Integration by parts is the idea that the integral of u dv is equal to uv minus the integral of v du. This is a standard calculus procedure. And when we apply it to this expression, just the right-hand side of the integrand, that is the one with the partial derivatives of the Lagrangian with respect to derivatives in A, we can expand this as the partial derivative of the Lagrangian with respect to the derivatives in A times the variations in A evaluated at the boundary of our spacetime hypervolume, minus the integral of variations in A times the derivative of the partial derivative of the Lagrangian with respect to derivatives in A. Confusing, right? Yeah, okay. But you know what? There's one thing that actually really helps us out here, which is that just as in the case of the telephone wire, the nudges vanish to 0 at the boundaries of our analysis. So we're only nudging the stuff inside the thing that we're looking at. I mean, if you want, you can use an arbitrarily large spacetime hypervolume, don't get me wrong, but we can go ahead and set the nudges equal to 0 at the boundaries. And what that's going to do is when we evaluate that term on the volumetric boundary of our spacetime hypervolume, it's going to go to 0 because the nudges are 0 out there, and so therefore that variation in A term, also known as the nudge, doesn't exist on the volumetric boundary of the spacetime hypervolume. So that's just a long-winded way of saying we don't have to worry about that boundary term, because all of the nudges happen within the region of spacetime that we're analyzing. Well, okay, so having done that integration by parts, and having set the boundary term to 0, we now see that we have a way of rewriting the second part of our integrand in a way that actually does have variations in the 4-vector just directly there, right? We popped it out of the derivative. And so now what we can do is if we combine that back in to that top integral up there, and go ahead and factor out a variation in the photon field, that is a nudge in the photon field, now we have an expression where we have some partial derivatives inside of the integrand, and that whole quantity is multiplied also inside of the integrand by a nudge in the photon field. But here's the thing, in this analysis, we're allowed to nudge the photon field any which way. At any point in space and time, we can give it any kind of directional nudge we want. And so the only way that delta S is going to be 0, that is the only way that the variation in action is going to be 0, is if that term that multiplies the nudge is 0. And this constraint, this differential equation, makes it so that the variation in action is 0, and therefore the principle of least action, or technically stationary action, is satisfied. So all we have to do now is solve this equation. Oh, by the way, this is called the Euler-Lagrange equation, and it's basically a way of writing the principle of least action in differential form. So with the Maxwell's equations, we have the differential form, we have the integral form, it's kind of the same thing in two different ways. Well, and so too, we have the principle of least action, which is kind of this macroscopic, global, integral kind of statement. But then we have the Euler-Lagrange equation, which is the local, microscopic differential equation that must be true in order for the action to actually be optimized. So nature doesn't somehow magically, psychically conspire to minimize the action, but instead the principle of least action is actually a global, kind of integral way of stating something which is actually a differential equation. And the equation we're showing here, the Euler-Lagrange equation, this is actually very generic, and you'll see it in all kinds of problems. Now, this particular form is what you get when you try to minimize the action with respect to variations in a four-vector field, but you'll see a very, very similar equation if you have like a scalar field or whatever the case may be. Well, now all we have to do is solve the Euler-Lagrange equation. How hard can it be? It's hard, but that's okay. Ask not for easier equations, but for stronger coffee. By the way, if you happen to have any coffee, now is the time to drink it. We're not done yet. We still got a ways to go. Okay, well, let's go ahead and write out our Euler-Lagrange equation. So this equation has a whole bunch of derivatives of the Lagrangian with respect to A and with respect to derivatives of A. And just a reminder, the letters mu and nu are both just placeholders for 0, 1, 2, and 3. In this equation, you can think of it as nu taking on any particular value, 0, 1, 2, or 3. And meanwhile, mu takes on all values and is summed over. So if you want, you can think of this as a 4-channel equation where each channel corresponds to a single value of nu. And then the right-hand side of each channel is actually the sum of 4 terms, one for each possible value of mu, 0, 1, 2, and 3. So now to solve this equation, let's write out our Lagrangian. Of course, now that we're experts on the Lagrangian of quantum electrodynamics, and we see how it arises from local phase symmetry of the Dirac field, we immediately recognize this term involving the electron field, and the interaction term involving both psi and A, and a term involving the kinetic part of the photon field, which is expressed with those Faraday tensors. Hold on, wait a minute now. Normally, when we write the Lagrangian, we write it in terms of mu and nu, but here we have it written in terms of alpha and beta. No worries, same exact concept. These are all just placeholders for 0, 1, 2, and 3. The reason we're writing it with alpha and beta now is because we already used mu and nu in the Euler-Lagrange equation. And what we have to do if we want to evaluate the Euler-Lagrange equation is we have to take all those derivatives and stuff with regards to the mu and the nu, and we have to apply that to each of the components of the Lagrangian with regards to the alpha and the beta components. So from a combinatorics perspective, there's going to be an enormous number of terms in this equation when we combine these two things. So don't be alarmed, but when you dice this up into scalar components, we're dealing with a 4-dimensional partial differential equation of like hundreds of terms. Fortunately, most of those are going to turn out to be 0, so that's nice. But anyway, thank goodness for the Einstein summation convention so that we don't have to write out all of those terms because that would take, like, forever. Einstein, that guy had a lot of good ideas. That's probably why everyone called him Einstein. Well, anyhow, let's go ahead and evaluate the left-hand side of our Euler-Lagrange equation first. So on that side of the equation, we're going to take the partial derivative of the Lagrangian with respect to the nth component of the 4-vector field. Now, before we take this partial derivative, let's look at the form of the Lagrangian and we'll notice a couple of things. First of all, we're taking a derivative with respect to the components of the 4-vector. So the term involving purely the electron field, that has no dependence whatsoever on the components of the 4-vector. So therefore, the partial derivative of that term with respect to the 4-vector is 0. That's going to vanish. So, nice. However, the next term, that one involving the charge and the interaction, that does directly depend on the components of the 4-vector. So that is going to stay in. That doesn't vanish out. But then the kinetic term, the term involving the Faraday tensors, remember, those are made out of derivatives of the 4-vector field. So when we're taking this partial derivative with respect to the components of the 4-vector, the term that depends on the derivatives of the 4-vector is not going to be directly affected by the derivative in the 4-vector itself. So therefore, that term is also going to vanish, because it only depends on the rate of change of the 4-vector in space and time, but not on the value of the 4-vector components. Okay, sweet. So we only have to worry about the interaction term, and that term directly depends on the components of A, where just go ahead and imagine that negative q, psi bar, gamma, alpha, psi, that's all a constant with respect to the component A alpha. And so therefore, if we evaluate this partial derivative, we can go ahead and pop that constant outside the derivative, and then we just have the partial derivative of the alpha component of A with respect to the nu component of A. Now, a partial derivative like that can only be one of two things. First of all, it's zero if alpha and nu are different. So if you're taking, for example, the partial derivative of the x component of A with respect to the y component of A, that's zero, because those are two totally different things, so, there's no derivative there. But by the same reasoning, if alpha and nu are the same, so suppose we take partial derivative of x component of A with respect to the x component of A, then that derivative is 1 because the derivative with respect to itself of anything is 1. And so this is interesting because what this means is that this partial derivative is going to delete everything except for when alpha equals nu. So if you examine this expression with the gamma alpha in the psi sandwich and the partial derivative, that's going to reduce to a gamma nu in a psi sandwich because that's the only term that remains that doesn't get deleted by the partial derivative becoming 0. Bear in mind, by the way, in this equation with the alphas, it's a sum over alphas because that alpha is repeated in the term involving the gamma and the partial derivative. But all of the non-nu possibilities for alpha get deleted by the partial derivative. Okay, anyway, I think I've belabored that point. So where does that leave us? Well, let's go ahead and recognize something. This term on the right, negative q, psi bar, gamma nu psi, in order to make sense of this term, we have to look to the definition of the forecurrent. The forecurrent, written in contravariant form, we can write as J with the nu upstairs, and that's going to equal the speed of light times the electric charge density combined with the electric current. And that is the charge of the particle times the speed of light times psi bar gamma nu psi. Okay, so now do a bit of pattern matching, and these terms only differ by a negative c. So I'll go ahead and factor this out, and you end up with 1 over negative c times the nth component of the forecurrent. Bear in mind, this equation has 4 channels for nu. Nu can be 0, 1, 2, or 3. We're not summing over nu, they're just 4 equations in parallel. One way to think about this is as an equation involving 4 vectors. So if you want to think about the partial derivative 4-vector of the Lagrangian with respect to the components of A, we can see now that that is equal to the forecurrent up to some factor of speed of light and a minus sign. This actually makes a lot of sense. Because think about it, how sensitive is the Lagrangian going to be on changes in the 4-vector field A? Well, just consider the nu equals 0 term, that is the time term of A. The sensitivity of the Lagrangian on the voltage is going to be proportional to the charge density, right? And likewise, if you consider the spatial parts of A, that is the magnetic vector potential, how much does the Lagrangian depend on changes in the vector potential? Well, that has to do with how much electric current you have somewhere. So this equation actually makes a lot of sense and lends itself to physical interpretation, so we're on the right track. Now let's go ahead and mosey on over to the right-hand side of our Euler-Lagrange equation. There we find a derivative of a derivative with respect to another derivative. Yo, dog. How are we supposed to deal with this? Well, let's look at the Lagrangian. If we start off with the electron term that only involves psi, and not A, then we can recognize that the derivative of that part of the Lagrangian with respect to the derivatives in A is going to be 0. So that term's not going to contribute at all to this mess of a derivative situation that we have, so we can safely ignore that. By the way, notice that in both sides of the Euler-Lagrange equation, we were able to ignore the first term involving only the electron's wave function. And the reason for that is that, remember, we're assuming that there is some arbitrary electron field psi, and we're letting A relax. That is, we're letting the photon field relax around that psi. And what that's going to do is that's going to give us the constraints on A that minimize the Lagrangian given some electron field. So at the end of the day, what that's going to give us is some equations about how the photon field has to be given some distribution of charge and current. And that is precisely what the inhomogeneous Maxwell's equations are. Okay, so moving on to the interaction term. Here, we notice that it is, from the perspective of partial derivatives involving A, it's basically a constant times A. But in this term on the right-hand side of the Euler-Lagrange equation, we're actually taking the derivative with respect to the derivatives in A. So even though the interaction term involves the values of the components of A, it doesn't actually involve the derivatives of A. So therefore, when we take the partial derivative of that term with respect to a derivative in A, the result is actually 0. See, because we're not taking the second derivative with respect to A, we're taking the partial derivative with respect to a partial derivative of A. So it's a little confusing, but hey, at the end of the day, what it means is we can safely ignore that interaction term. So that's wonderful. But now we turn our attention to the kinetic term of the photon field. And we see these Faraday tensors. And what are Faraday tensors made out of? A bunch of derivatives in A. Shoot, that's exactly what we've got to take the derivative with respect to, so this term is not going to vanish. Okay, so now we get to evaluate this messy derivative of this Faraday tensor thing. Well, alright, let's do it. So the first thing we'll do is we'll notice the negative 1 over 16 pi. That's a constant, so let's just go ahead and pull that outside of the derivative. And now we can write this expression involving the derivatives and just the product of those Faraday tensors. And now, what we're going to do is let's go ahead and combine the left-hand side and the right-hand side of the Euler-Lagrange equation. We'll bring these two things together. So on the left side, we have that factor involving the electric forecurrent. And on the right side, we have this mess of a derivative with the Faraday tensors. Well, let's go ahead and stick them together. And I'll do a little switcheroo, so the left is now the right and the right is now the left, but it's all good. Okay, well, now we have a whole mess to deal with because there's derivatives and Faraday tensors and forecurrents and whoa. But you know what? This equation, it actually smells like the inhomogeneous Maxwell's equations, because think about it. What is the Faraday tensor? It's made out of derivatives of the potential. And what is the electric forecurrent? It's electric charge and electric current. And so what this equation is telling us is that there is some relationship to the way that the photon field flops around and the electric charge and current. And it turns out that's going to be the inhomogeneous Maxwell's equations. So now all we have to do is unfold and simplify this equation. Think of it like a Rubik's Cube, it's all scrambled up, but we just got to make it clean. And when we clean it up, we'll find the Maxwell's equations that we're looking for. And a bonus surprise equation, which I'll tell you about in a moment. All right, well, we've got no other choice than to start to evaluate this derivatives with the F terms, and it's okay, well, we can apply the product rule, and we're going to go ahead and break up that derivative. So first, we're going to let the derivative act on the downstairs Faraday tensor, then we're going to multiply that by the upstairs Faraday tensor, and then for the second term, we're going to have the downstairs Faraday tensor multiplied by the derivative acting on the upstairs Faraday tensor. So that's like your standard application of the product rule. While we're at it, let's go ahead and multiply everything by negative 16 pi, just to scoot that constant on over to the right side of the equation. And okay, so what should we do next? Well, if you look at these two terms, the derivative of the F and the F times the derivative of the F, these two terms actually look kind of like the same thing, right? I mean, one of them is derivative of downstairs times upstairs, and one of them is downstairs times derivative of upstairs. But as it turns out, these actually are identical. The reason being that the only difference between the downstairs and the upstairs, that is the covariant and the contravariant, is just the minus sign on some of the terms. And when you multiply the upstairs and the downstairs Faraday tensors, you get the same thing, whether you do the downstairs first, then the upstairs, or the upstairs first, then the downstairs. The point there is that the derivative isn't going to change that fundamental fact because the derivative operator isn't going to change the signs of any of the components asymmetrically depending on whether it's covariant or contravariant. So that's all good. So what that means is that we can go ahead and let those terms absorb into the same term. It doesn't matter which one we pick. We'll just pick the first one because why not? And then we pick up a factor of 2 on the outside of that equation. So they just merge together. All right, well, we're getting somewhere, but we still have this very complicated thing, partial derivative of the Faraday tensor with respect to the partial derivatives of the 4 potential times the Faraday tensor. Oh my gosh. What have we gotten ourselves into? What do we do to deserve this, you know? Are we put on this earth just to suffer? Ugh. But we're in too deep now. We can't quit. We're actually almost at the end of the derivation, so bear with me here. Well, first of all, might as well go ahead and divide by 2. So the 2 goes away and the 16 pi becomes 8 pi. And now what we want to do is let's go ahead and get rid of the Faraday tensor term in the derivative. And instead, we're going to write that explicitly in terms of partial derivatives of the 4 potential A. Because remember, that's all the Faraday tensor is. It's made completely out of the 6 ways that A can manifest without violating the phase symmetry of the Dirac equation, you know? And so therefore, to take the derivative of the Faraday tensor, all we're doing is taking the derivatives of the derivatives, and then there's a minus sign because there's another derivative because the Faraday tensor is a derivative minus a derivative. You know, it's hard to say, but you see what it is, right? Okay. But now the problem is we have quite a predicament here because we still have an equation involving alpha, beta, mu, and nu. And so each of these terms that involve all 4 of those letters actually represent 256 terms. I think 256, because you got 4 times 4, that's 16 times 4, 64 times 4, 256. Yeah, so each one of these terms is actually 256 terms. Now, nu is any possibility. So remember, we have 4 channels in nu, but mu, alpha, and beta we're all summing over. So think of this as 4 equations in parallel, or a 4-vector equation if you like. But then within each of those equations, all of these terms involving the alpha, the beta, the mu, the nu, each of those is going to be 64 terms per equation. So, you know, if you're one of those people like me where the first time you see the Einstein summation convention, you think, oh, this is kind of cryptic and burdensome. Well, I hope now you see the mess that it saves us from. Imagine writing that all out by hand. No, there's no way. Okay. Anyway, how do we actually solve this? Well, here is some very good news. This term, the derivative of the partial derivative with respect to the other partial derivative, this is almost always 0. I think like 15 out of 16 times it's 0. Because the thing is, if you take the partial derivative of a partial derivative with respect to another partial derivative, it's just like before, remember when you had the partial derivative of one component of A with respect to another component of A? Usually, there's no connection there. That's 0. They don't depend on each other. They're different independent things, right? And the only way that's not the case is if you're taking the partial derivative of a partial derivative with respect to the other partial derivative that is in fact itself. I don't know if that makes sense. Anything you take the partial derivative with respect to itself is 1. And so what that means is that there are a few cases where this partial derivative is 1, and that is when alpha equals mu and beta equals nu. Because then on both sides of this partial derivative, it's the same thing. It's the derivative of a thing with respect to itself. So what effect does that have on the equation? Well, just like we saw when evaluating the left-hand side of the Euler-Lagrange equation, and the partial derivative term deleted everything except for the nu component. Well, here what it's going to do is this complicated partial derivative term is just going to delete everything except for the mu nu component. On the left term, or on the right term, you see the betas and alphas are switched, so that one is going to delete everything except for the new mu component. But in either case, at the end of the day, look how wonderfully simple these become. The partial derivative just vanishes, and it also takes out with it a lot of the different possibilities for alpha and beta. We see now that they're just mu and nu. And so finally, now we're back down to an equation with only 2 of these indices, so we don't have to worry about all the crazy combinatorial explosion that we had to deal with earlier. Now the equation actually simplifies quite a bit. And now we can actually go ahead and simplify this further, because remember that the Faraday tensor is defined as just the partial derivative of this component of A with respect to that component of spacetime, minus the partial derivative of that component of A with respect to this component of spacetime. And so if you switch mu and nu around, then you can see that f nu mu is the same as just negative f mu nu. In other words, the tensor is antisymmetric. So what that means is that if we have f mu nu minus f nu mu, we can absorb those together and write that as 2 f mu nu. Now we're getting something really nice. I mean, this is, very elegant. But we can clean it up just a little bit by dividing by 2. This, my friends, brings us to the equation that we were seeking. This is a beautiful, profound equation. It's one of my favorite equations of all time. And why is that, you might ask? Because this one equation is actually both of the inhomogeneous Maxwell's equations. It's both Gauss's law for electricity and Ampere's law with Maxwell's addition. But look, it's like one equation. It's beautiful. And don't worry, we're going to unpack that in a second. I'm not going to leave you hanging. But I just want to linger on this for just a moment and point out the fact that not only have we accomplished what we set out to accomplish, that is, deriving the inhomogeneous Maxwell's equations, but we did it in a way that unifies them into a more elegant equation, which is very nice, very deep. So in one equation, we get Gauss's law for electricity, but we also get Ampere's law with Maxwell's addition. Amazing. But wait, there's more. This equation also implies that electric charge is locally conserved. I mean, it's like, whoa. So this is why we do variational calculus. The pain is worth it, because it's such a powerful method and it gives us such beautiful results. Okay, so let's go ahead and unpack this equation. So this equation we just derived, it's actually 4 different equations in one. One equation for each value of nu. Or another way of thinking about it is this is a 4-vector equation. And as it turns out, the nu equals 0 component of this equation is Gauss's law for electricity. And now all we have to do is translate this equation into the language of derivatives and charge and electric fields and all that stuff. So I'm going to put all this information here just for reference, so that we can refer to this while doing this translation. So first of all, let's go ahead and expand the equation and write out each one of those terms. Now right away, we notice there's this term involving f00, and that's going to equal 0, because if you look at the Faraday tensor, f00 is 0. So that term goes away. What we're left with is this sum over derivatives of f10, f20, and f30. And first, if we look at this term involving partial 1, f10, we see that partial 1 is the derivative with respect to x, and f10 is the x component of the electric field. So therefore, that term becomes the partial derivative of the electric field with respect to x. Likewise, for the next term, we have the partial derivative in y, acting on the y component of the electric field. So we end up with the partial derivative of the y component of the electric field with respect to y. And you can probably see where this is going, because the third term, we're going to have the partial derivative of the z component of the electric field with respect to z. Now, on the right-hand side of the equation, we recognize that J0 is the speed of light times the charge density rho. So when we plug that into the equation, the speed of light cancels out with the 1 over speed of light, and we end up with 4 pi times the charge density. Now all we have to do is recognize that the left-hand side of this equation is the definition of the divergence of the electric field, and we can write this equation as the divergence of the electric field equals 4 pi times the electric charge density. And that is none other than Gauss's law for electricity. Wow, what a deal. It's all coming together. So now we've got 3 Maxwell's equations. By the way, this equation you can also write in integral form using the same math that we saw earlier with Gauss's law for magnetism. Just apply the divergence theorem and you'll end up writing it in integral form. All right, so now we've got 3 out of the 4 Maxwell's equations. And to get the last equation, all we have to do now is look at the nu equals 1, 2, and 3 components. So here we're going to have 3 equations in parallel. And if you like, you can think about this as an equation involving 3 vectors. And the way I've written it here emphasizes the 3-vector perspective. Now let's go ahead and look at this term partial mu f mu1, and just go ahead and expand that out unpacking the Einstein summation convention and just expanding it as a sum over the different possibilities for mu, and you get partial 0, f01 plus ... And right away, we see that one of those terms is f11, and if we look at the Faraday tensor, we see that f11 equals 0, so that term goes away, which is nice. And then if we follow the same procedure for that second component, the partial mu f mu2, again, we expand it as a sum over the different possibilities for mu. And now we find that there is a term including f22, which is 0, so that term cancels out. Finally, we're going to go ahead and write out that third component, partial mu f mu3, expand that as a sum over the different possibilities for mu, and we see that the f33 component cancels out. Now then, if we take that top equation, and we expand each of those partial derivative f terms in terms of the sums that we've just written out, we can write out this equation with a vector on one side and a vector on the other side. And here again, we can use the definition of the foregradient as well as the Faraday tensor to translate this into an equation involving derivatives of different components of the electric and magnetic fields. First of all, if you look at the derivative terms, you can see that partial 0 is 1 over c partial t. Likewise, partial 1 is partial x, partial 2 is partial y, and partial 3 is partial z. And then if you look at the various components of the Faraday tensor that start with 0, so f01, f02, f03, you'll see there the negative components of the electric field. And if you look at the terms that don't start with 0, so f21, f31, f12, f32, f13, f23, you see that these are the components of the magnetic field, and some of them have a minus sign and some of them don't. So now on the left side of the equation, we have this vector involving a whole bunch of derivatives of components of the electric and magnetic fields. Let's go ahead and separate that out into a vector with just the magnetic stuff and a vector with just the electric stuff. And now if you look at that magnetic term, you'll recognize that as the curl of the magnetic field B. And if you look at the electric term, you'll recognize that as negative 1 over c times the time derivative of the electric field E. And what do you know? Sure enough, this is Ampere's law with Maxwell's addition. Wow. And that brings us to 4 out of 4 Maxwell's equations. And by the way, if you want to convert this to the integral form, you can use the same methods that we used for Faraday's law of induction. Well, okay, you know what? Now we have actually done something very profound. And if you've made it this far in the video, you should be proud of yourself because you've leveled up. Because now you know where Maxwell's equations come from. You don't have to take it on faith anymore. You don't have to say, okay, these are like these sacred equations that I just have to believe. No. Well, okay, you still have to believe in local phase symmetry of the Dirac field, but that's like one thing. And now you see where these 4 things come from. So philosophically, this is the next level. You know, I know in our culture, it's kind of fashionable to think of physics as like this dry, boring, esoteric, sterile endeavor. But this is actually a thoroughly shamanic exercise. Like when you really incorporate this math and these ideas into your worldview, it's amazing. You're like, wow, all these different electromagnetic phenomena arise from this simple principle. Like, are we living in a kaleidoscope? I mean, what is going on here? Why? It's like, oh, I'm at a loss for words. So that's my cue to move on to the next topic. Oh, I almost forgot. So in addition to the inhomogeneous Maxwell's equations, the same equation that we just derived with the partial mu f mu nu equals 4 pi over c j nu, well, it's kind of a tongue twister. Well, anyway, it also implies that electric charge is locally conserved. And local charge conservation is just the idea that the rate of change of charge density somewhere in space is going to be balanced by the divergence of currents at that location in space. This actually has a very intuitive interpretation. All this is to say that if you want to remove charge from some location, it has to flow out of that location. Or conversely, if you want the amount of charge somewhere to increase, it has to flow in to make it increase. So you can think of local charge conservation as a way of saying that charge cannot teleport. And what's really neat is if you look at our relativistic notation, we can write this a lot more simply as partial mu j nu equals 0. And here, because nu appears twice, we're summing over that term. So in other words, partial 0 j0 plus partial 1 j1 plus partial 2 j2 plus partial 3 j3 equals 0. So that's just another way of writing the condition of local charge conservation. And you'll notice that this is a Lorentz invariant property. All inertial observers are going to agree that this quantity is 0, because the expression combines the covariant foregradient with the contravariant current. So to prove that electric charge is locally conserved, we just have to prove that partial nu J nu equals 0. And to do that, we can take our equation, and now what we want to do is we want to substitute that J nu into the equation partial nu J nu and see if it actually does equal 0. So when we write out partial nu J nu, we can write that as partial nu C over 4 pi partial mu F mu nu. So many mu's and nu's, it's hard to say. Anyway, so we can pull out the C over 4 pi as a constant, and now what we have is the derivative of an F mu nu. And because both nu and mu are repeated in this term, this expression is actually a sum over all of those different indices. So we're going to have 16 terms here. And each one of those 16 terms is going to have the form of a second derivative of a component of the Faraday tensor. And as it turns out, because the order of the differentiation doesn't matter, and because of the antisymmetry of the Faraday tensor, that is because F mu nu equals negative F nu mu, these 16 terms are all going to cancel out in pairs, and the result is going to be 0. So for example, consider the case where nu and mu can be 0 and 1, or 1 and 0. In that case, you have two terms, depending on which one is 1 and which one is 0, and you can look at that as partial 0, partial 1, F1, 0, plus partial 1, partial 0, F0, 1. But because partial 0, partial 1 has the same effect as partial 1, partial 0, and because F0, 1 equals negative F1, 0, we can write the second term there simply as negative partial 0, partial 1, F1, 0, which cancels out with the first term, and so you end up with 0. And if you try that with all the different combinations of mu and nu, you'll see that they'll all cancel out in pairs. And so yes, in fact, this expression is 0, and therefore, electric charge is locally conserved. Now, this derivation is interesting. It's sort of an implicit constraint, because we set out to say, okay, we have some psi, and we're going to calculate what must be true about A in order to relax the QED Lagrangian for that psi. So it's a little bit strange that what we have now is actually a constraint on J, which, because J is born of psi, that's also a constraint on psi. This constraint is required in order for the consistency of these equations to all hold together, And from our current viewpoint, this might seem like something of a mysterious result. But if you're interested, you can derive this from scratch using global U1 phase symmetry of the Dirac field as the continuous symmetry and plugging that into Noether's theorem. And that'll give you a proof that probability for current is conserved. But it's philosophically the same basic thing, so. Well, anyway, I just mentioned that in passing, but yeah, that's another cool result, is that electric charge must be locally conserved. All right, so we've come a long way. Now we've got all the Maxwell's equations, and we've even got local charge conservation. But we still haven't yet derived the Lorentz force law. So let's do that. All right, well, so to derive the Lorentz force law, all we have to do is apply the Euler-Lagrange equation to a relativistic particle that is immersed in the 4 potential. Now for this derivation, we're going to take as a starting point the Euler-Lagrange equation for a relativistic particle, as well as the Lagrangian for a relativistic particle in a 4 potential. And from these principles, we're going to be able to derive the Lorentz force law. But first, let me say a few words about where these principles come from. All right, let me put this little note down here. So tau is the particle's proper time, that is, the time as measured by the particle. And x mu is the contravariant for position, so x mu as a function of tau represents the particle's path through spacetime. And if you take the total derivative of x mu with respect to tau, that gives you the particle's 4 velocity, and we're going to write that as u mu. Griffiths uses eta for the 4 velocity, but we'll use u. Either one is fine. So if you're interested in the derivation of the Euler-Lagrange equation for the relativistic particle, you can pause the video here and explore this in detail. But I'm just going to gloss over this for now for a couple of reasons. First of all, this derivation is remarkably similar to what we've already done for the inhomogeneous Maxwell's equations. It relies on the same basic concept of putting nudges on the equations and integrating my parts and taking out the boundary terms. And anyway, at the end of the day, remember how the Euler-Lagrange equation is like a microscopic version of the macroscopic principle of least action? So, in physics, you often just start with the Euler-Lagrange equation, and it's understood that this comes out of the principle of least action. So we're just going to go ahead and start off with the Euler-Lagrange equation, and in the interest of time, we're not going to reiterate the process that gets you from the principle of least action to the Euler-Lagrange equation. Okay then, moving on to the Lagrangian, let's first take a look at the mass term. So the mass term in the Lagrangian is going to be -1/2 m times u nu. And what that is just -1/2 times the mass times this Lorentz invariant quantity that has to do with the 4 velocity of the particle. Now, to derive this in a rigorous way is actually surprisingly complicated and tedious, especially in the form that I'm currently showing it in with this quadratic form in the 1/2. There's a lot of nuance and details behind there, and I worry that we'd go off on too much of a tangent if I try to derive that here. So let me just say a few things in passing. The first is that this mass term is about as simple as it can possibly be. There's, if you look at what it's made out of, there's a factor of m, which, we expect a factor of m. And then there's a Lorentz invariant quantity, u nu, made out of the 4 velocity. And, so that kind of makes sense too. By the way, that quantity equals the speed of light squared. But it's worthwhile to write it out in this form so that we can derive equations of motion from the Lagrangian. Okay, well anyway, if you're curious about where this term comes from, there's actually a really good Wikipedia page called Relativistic Lagrangian Mechanics, and that goes into a lot more detail, so check that out if you're interested. But for now, let's just go ahead and accept that term, and we'll notice also it bears no resemblance to the Lorentz force law, so even if you're a little skeptical of where does this come from, well, it doesn't have like E plus V cross B in there, so we're not like sneaking in the Lorentz force law. So I hope it's not too unsatisfying that I didn't provide a rigorous derivation of this term right now. Okay, well, but to make it up to you, I will provide a decently rigorous derivation of where the interaction term in the Lagrangian comes from. So to get this term, what we do is we start off with the interaction term in the Lagrangian density of quantum electrodynamics. And as we've seen, that term is just -q psi bar gamma nu psi a nu. Now, if we write that in terms of the 4 current, which is J nu equals CQ psi bar gamma nu psi, then we can write the interaction term of the QED Lagrangian as -1/c J nu a nu. And now what we have to do is we have to take this to the classical limit in the sense of localizing the particle, zooming out, thinking about like the big picture of, okay, we're in some place and there's some 4 potential, and relative to the changes in the 4 potential, our particle is very small and very localized. And so if we want to get the Lagrangian, that is the integral of the Lagrangian density over spacetime, for the interaction term, all we have to do is integrate over space, this 1/c J nu a nu. Now, while we're doing that, we can notice, well, okay, -1/c, that's a constant, pull that outside the integral. But also, because the particle is going to be sharply localized, the 4 potential is not going to vary from one side of the particle to the other, right? If we're dealing with basically a point particle, then there's just going to be some value of a nu there, and so we can pop the a nu outside of the integral as well. Then, if you think about what it means to integrate the 4 current over some volume of space, you see that that ends up being just the charge of the particle times its 4 velocity. And so if we put the expression q u nu into the equation, we end up with the interaction term for the Lagrangian of -q/c u nu a nu. And so here we can see that this interaction term does follow directly from the Lagrangian of quantum electrodynamics. And that's really the important thing, right? Philosophically, if we want to show that electromagnetism comes out of local phase symmetry, we want to use all of the ideas we've developed so far. And in particular, if we're wondering how the electric and magnetic fields are going to push around a charged particle, then it's important that at least for sure the interaction term that we're using in our Lagrangian is going to be the classical limit of the interaction term in the Lagrangian density of quantum electrodynamics. All right, well, let's go ahead and solve the Euler-Lagrange equation, first by evaluating the left-hand side. On that side of the equation, we have the partial derivative of the Lagrangian with respect to the 4 position. And if we plug in the Lagrangian, we can write that as the partial derivative with respect to x mu of the Lagrangian, which contains a mass term and also an interaction term. By the way, sometimes you'll see the Lagrangian multiplied through by a minus sign so that these terms are both positive. You'll see that in some derivations. And that's doable because imagine if you multiply your Lagrangian globally by some constant, that's not going to change anything about the governing equations that the Lagrangian gives you, because when you optimize it, a global scale constant is just going to wash out. It doesn't have any effect on anything. But anyway, we'll just go ahead and keep the minus signs in for simplicity. All right, well, now to evaluate this expression, first, let's go ahead and start off with the mass term that I've highlighted here in orange. We'll make the observation that the partial derivative of the particle's covariant velocity with respect to the contravariant position is 0. And notice in this expression, the 1/2 and the m are constants, so they're just going to multiply the derivative. So when you think about this derivative, you can ignore those. They are not really relevant or interesting. And when you take the derivative of the rest of the expression, bear in mind that the velocity here is to be evaluated as a function of tau, the proper time. And so the partial derivative with respect to x mu is actually going to be 0. All right, and now if we shift our attention over to the interaction term, which I've highlighted in green, we can see that when we take a derivative with respect to x mu, q over c, that's a constant, of course, but also u nu as a function of tau is going to be a constant relative to the partial derivative of x mu, and so we can write that expression as q over c u nu, partial a nu, partial x mu. So at the end of the day, what we end up getting for this expression is that the partial derivative of the Lagrangian with respect to x mu is negative q over c times u nu, partial a nu, partial x mu. So that is the left-hand side of the Euler-Lagrange equation. Moving on over to the right-hand side, we want to take the total derivative with respect to the proper time of the partial derivative of the Lagrangian with respect to the velocity. So let's plug in the definition of the Lagrangian. And once again, we'll focus first on the mass term, and then we'll focus on the interaction term. And first, we'll evaluate the derivative with respect to the velocity, and never mind for the moment the derivative with respect to tau. So evaluating the derivative with respect to the velocity of the mass term, we recognize that negative 1/2 m is a constant, so we pull that out. And then the term u nu, we're going to go ahead and split that up using the product rule. And at this point, I'll just go ahead and drop the parentheses as a function of tau. Now if we look at the interaction term, when we take the derivative relative to the velocity, we see that negative q over c is going to be a constant, so that comes out of the derivative. And we also notice that a nu as a function of x is going to be a constant relative to the partial derivative with respect to u mu. And so that's going to come out as well as a constant. And finally, the u nu term, that's going to stay in the derivative, and so we end up with the partial derivative of u nu with respect to u mu. Okay, now if we look back to the mass term, let's go ahead and evaluate the expression that we got as a result of the product rule. And we'll notice here that these two terms look very, very similar. And also the partial derivative looks like one of those things where it's either 0 or 1, and so it's going to turn off most of the indices except 1. And so, yeah, if you look at the partial derivative, it turns out that the partial derivative of u nu with respect to u mu is going to be 1 only when nu equals mu. And so therefore, that whole expression reduces to the specific case of u mu. All right, and likewise, the same thing is exactly true when it comes to the other term, but here let's go ahead and switch the indices around. So we have an upstairs u nu times the derivative of the downstairs u nu, and we can just go ahead and switch those around. So instead we can have the downstairs u nu times the derivative of the upstairs u nu, because in both cases the minus signs end up working out the same way. And then here we have the same expression as before, and so we recognize that as u mu. So in that expression, in this sum of the green and the orange terms, we end up having 2 u mu. So we multiply that through, it cancels out the 1/2, we pull the negative sign outside the time derivative, and we end up with the negative time derivative of m times u mu, plus something, plus the interaction something. So what is that interaction something? So if we examine this derivative, we also see a partial derivative of u nu with respect to u mu, and that's usually going to be 0, but it'll be 1 when nu equals mu, and so that term has the effect of converting that expression into simply q over c a mu. Alright, so we're getting somewhere. The equation is starting to simplify. So here let's go ahead and recognize the term mu mu as the kinetic force momentum p mu. And now let's go ahead and split out these terms in the derivatives. So we'll start off with the negative derivative of the momentum with respect to the proper time, minus whatever happens when we apply the derivative to the interaction term. So let's go ahead and do that. Well, first of all, the q over c, that purple term, that's a constant, so that's going to be on the outside of the derivative. And the real question is, what is the derivative of a mu with respect to the proper time of the particle? Now here this is tricky because it's not the partial derivative of a mu with respect to time. What it is is the total amount of change of a mu that the particle sees as it's moving through spacetime. And so to calculate this total derivative with respect to the proper time, we have to imagine from the particle's point of view, what changes does it see as its clock ticks forward? And so what that proper time derivative is going to be is the product of the partial derivative of a mu with respect to x nu times the total derivative of x nu with respect to tau. And by the way, I know you're not supposed to pretend that derivatives are fractions, but if you pretend it's a fraction, this kind of makes sense, you know? Well, anyway, we can recognize the total derivative of x nu with respect to tau as the definition of the four-velocity u nu. And therefore, we can write this expression, having taken the total proper time derivative, as q over c partial a mu partial x nu times u nu. So now that we have the left-hand side and the right-hand side of the Euler-Lagrange equations, we can stick them together. And now if you look at it, you can kind of parse it up and see like what are the different things in this equation. We've got some q over c's, we've got some u nus, we've got some partial derivatives and stuff. And so we can write this equation in a cleaner way. We can move the blue term over to the left and the yellow term over to the right and factor out the orange term and factor out the purple term. And we end up with an expression for the total derivative of the kinetic four-momentum with respect to the proper time in terms of charge and in terms of partial derivatives of A and in terms of the four-velocity of the particle. So that's cool. That really feels like we're getting to the Lorentz force law. That feels like we're on the right track. And you know what's really neat is, check this out. So look at that term in the brackets. We have partial mu A nu minus partial mu A mu. Well, that's just our good old friend, the Faraday tensor, F mu nu. So we can write this equation as q over c F mu nu u nu. Wait, hold up. Q over c F mu nu u... Man, this is tough to say. Q over c F nu mu nu. Okay. So it ends up being just the charge of the particle divided by the speed of light times the field strength tensor multiplied by the four-velocity of the particle. And as it turns out, this is the Lorentz force law in relativistic notation. And of course, we're going to unpack this in a second, but before we do, I just want to emphasize the simplicity of this equation. What we have on the left side is basically a time derivative of momentum, so that's like the definition of force. And what we have on the right side is kind of the simplest thing it could be. I mean, there's a factor of charge, there's a speed of light to make the units make sense, there's the field strength tensor, which is, a relatively simple object that we can make out of the various ingredients of our theory, and we also have the four-velocity of the particle. So this is not like some crazy, complicated equation. And also, it's more elegant than what you normally see for the Lorentz force law, where you have that term with the electric field and the cross product between velocity and the magnetic field, and it's like, what's going on there, and what are these fields, and why does velocity come into the picture? It's like, okay, in the relativistic version of the equation, these kinds of questions don't really come up. It's more like, oh, wow, look at this neat little elegant result. So anyway, what we have here is yet another example of relativistic notation making the laws of electromagnetism look a lot more concise and elegant and unified. Okay, so now we're going to see how the Lorentz force law pops out of this relativistic equation, dp mu d tau equals q over c F mu nu F nu mu nu nu. So first what we'll do is, let's go ahead and expand that term involving the f's and the mu's and nus and u's, and we'll just write that out as a sum over each possibility for nu, because those indices are repeated, so we're summing over nu, and you can see that what we have here is an equation for the muth component of the proper time derivative of the four-momentum. So let me put a bunch of stuff here for reference, and we'll go ahead and translate this into an equation about forces in x, y, and z. First off, let's go ahead and consider the mu equals 1 component of the equation. So we just write out the equation, and we replace mu with 1. Now if we look at all the stuff on the right, we can see that those Faraday tensor terms are going to be an electric field and a zero and some magnetic field terms. And the components of the four-velocity are going to be the Lorentz factor gamma times the speed of light for the time component and negative velocity components for the 1, 2, and 3 components. And the minus sign comes from the fact that this is the covariant four-velocity. Okay, so if you substitute those into the equation, we get the equation shown here, and I've gone ahead and pulled out the Lorentz factor outside of the equation to clean it up a little bit. And now what we're going to do is we're going to pull the gamma factor, that Lorentz factor, over to the left-hand side of the equation, So we're going to have 1 over gamma times the derivative of the x component of the momentum with respect to the proper time. And then if we write out all these blue terms and clean it up a little bit, we see that that equals some expression involving electric and magnetic fields and components of the velocity. So this is looking very promising. I think we're on the right track. Now, to make sense of this equation, we have to use the fact that a differential step in coordinate time is going to be the Lorentz factor gamma times a differential step in the proper time. And if we make that substitution into the left-hand side of this equation, we get an expression for the derivative of the x component of momentum with respect to the coordinate time, which is exactly the force in the x direction on the particle. So that's awesome. It's like, this is the moment of truth. We're finally going to see if we get the right force. So now take the right-hand side of that equation, go ahead and distribute through a 1 over c, so that's going to cancel out the c on the ex, and that's going to give us a 1 over c on the magnetic and velocity terms, and then we're going to recognize bz vy minus by vz. That is the x component of the cross product of the velocity and the magnetic field, just by pattern matching, right? Just by looking at the definition of the cross product. And so this is indeed the x component of the Lorentz force law. Wow, we've done it. Well, okay, let's just make sure. So let's repeat the argument with the mu equals 2 component, and we can see that with exactly the same reasoning, we can derive the y component of the force. And yes, indeed, that ends up being the y component of the Lorentz force law. Okay, so 2 out of 3. I really think this is going to be the Lorentz force law. Let's go to mu equals 3. And again, same exact reasoning. And as you can see, if you follow through these equations, yep, we end up with the z component of the Lorentz force law. Now we pull these all together into a vector, and what do you know? There it is, the Lorentz force law, derived from local phase symmetry of the Dirac field. Wow, how good does it feel to finally get the Maxwell's equations? That's one thing, but now also the Lorentz force law. That pretty much completes the big picture of showing how U1 symmetry gives rise to electromagnetism. So, man, it feels good to finally get to this point in the video. Okay, hey, well, before we wrap up, there's a couple of miscellaneous things I wanted to say that didn't really fit into the flow of the video, but are kind of interesting little tangents, so I want to mention those briefly. And I want to talk about some mysteries, too, while we're here. Because, physics is not done yet. There are still open questions and problems and mysteries, and it's important to reflect on those, too. And, now that we've done all this math and stuff, we're in a really good position to wax philosophical about what it all means. So we'll do that for a few minutes before we get going here. So in this video, I have intentionally avoided the topic of the covariant derivative, but I know that if I don't mention it, at least in passing, I'm going to get a million comments like, hey, why didn't you talk about the covariant derivative? Like, how can you talk about gauge theory without talking about the covariant derivative? So, okay, let me just say a couple of words about it. First of all, I think that when you're first getting into electromagnetism as a gauge theory, you should not worry about the covariant derivative. This is a concept that I think hides more than it simplifies. And when you're trying to get oriented in all of this and kind of feel your way around and get familiar with stuff, in my opinion, the covariant derivative is kind of a cryptic thing that doesn't give you a ton of benefits until later on, especially if you're thinking in terms of fiber bundles and really getting into it. But at first, it's not super useful in my opinion. Well, anyway, it is something you should be aware of. And the idea is basically just to redefine the derivative operator relative to the 4 potential. So you can say that capital D mu is just going to be partial mu plus I times Q over H bar C, A mu. And when you do this, then you can write the QED Lagrangian in a simpler way, where you have a capital D instead of a partial, and you don't have to explicitly write the interaction term because it's been absorbed into the definition of the covariant derivative. Anyway, look, take it or leave it. You don't have to use it if you don't want to. I like to write out the interaction term, but I can see if you're working with fiber bundles or something where like the interaction term is kind of unnecessary to write and you want to think about it in a more elegant way. Okay, I get it. I'm not hating on the covariant derivative. I'm just saying it's kind of optional, at least from an introductory perspective. So, okay. Oh, I have to say a few words about the gauge invariance of the 4 potential and how it relates to the local phase symmetry of psi. So, in classical electromagnetism, if you have some electric field and some magnetic field, the 4 potential can be modified while still describing the same situation. So it's kind of redundant, like there can be multiple different 4 potentials that correspond to the same electric and magnetic fields. So, the classic example is that voltage can be raised or lowered by some uniform amount without changing anything. because you can define ground to be whatever you want it to be, right? So what matters is the change in voltage from one place to another. It's not really the absolute voltage itself. So that is like a classic example of gauge invariance. But that concept can be generalized, and actually, if you take the 4 potential, you can add to it the 4 gradient of any arbitrary scalar field. You can have a scalar field lambda that's flopping around arbitrarily. And you can show, using the definitions of E and B in terms of derivatives of A, that this is in fact the case. And one of the questions you have when you first learn electromagnetism is, why? Like, that's weird, that the 4 potential is loose like that. It's like, where does that come from? But from the perspective of gauge theory, we can see that it comes directly from the local phase symmetry of psi. So for example, if you multiply psi by e to the I theta, where theta is some function of spacetime, then as we've seen earlier in the video, the 4 potential is going to have to transform and pick up a factor of negative h bar c over q times the 4 gradient of theta. But let's go ahead and absorb negative h bar c over q times theta simply as lambda, because that's just a scalar, right? So then the transformation is a mu becomes a mu plus the 4 gradient of lambda. But that's exactly what the gauge invariance or the gauge freedom of the 4 potential is anyway. And so the lesson there is that the gauge freedom in the 4 potential that you learn about in classical electromagnetism is literally just the same thing as the local phase symmetry in psi, viewed from the point of view of A. So that's like one more thing that's not a mystery if you start with the perspective of local phase symmetry. You see that it's just like how it is. So now I'd like to talk about the mystery of the fine structure constant. So one thing that gauge theory doesn't tell us at all is why Q should have the value it has, right? Why the charge should have the value it has. Now it's a little bit subtle and nuanced because from a purely symmetry-oriented perspective, we can say, well, naturally, wouldn't it make sense if Q was 1, and then we just had some weird constant on the photon's kinetic contribution to the Lagrangian? But then you see that it's the same mystery, because then the question becomes, well, why does that constant have the value it has? But at the end of the day, the mysterious ratio is the ratio between the strength of the electromagnetic interaction and the energy of a photon. And so one really clean way to look at this ratio is to just make a fraction, and on top, you put the energy required to overcome the electrostatic repulsion of 2 electrons. So if you bring them together from infinitely far away, and you pull them together to some distance d, then the energy required to do that in Gaussian units is q squared over d. And then we're going to divide that energy by the energy of a single photon whose wavelength is 2 pi times that distance. Or in other words, the angular wavelength is the distance that we've brought the electrons together. And the energy of that, given by the Planck relation, is hc over lambda. And so when you simplify this, you end up with q squared over h bar c in Gaussian units. In SI units, you also have a 4 pi epsilon naught, but that's okay. Regardless of your system of units, when you calculate the value of that expression, you get a constant. And the constant is this weird, mysterious number that has no units. It's just 0.0072973525643. Although usually people remember the value of its reciprocal, which is about 137.035 something. But what nobody knows is, where does this number come from? What determines this number? Why is it what it is? Why is electromagnetism as strong as it is? No one knows. And look, don't just take my word for it. Let's hear what Dirac has to say.
There is the problem of explaining the fine structure constant, the number 137, which plays an important role in physics. And the question is, why should it be 137 instead of some other number? That has not been explained at all, and I feel that it is necessary to get an explanation of that before one will make an important advance in understanding atomic theory.
So now that we've seen that local phase symmetry gives rise to electromagnetism, we can ask the question of, what happens if we break local phase symmetry? And so, for example, this is what happens in a superconductor. But don't worry, it's not as destructive as it sounds. Actually, the local U1 phase symmetry still applies to the laws of physics in a superconductor, but the superconducting ground state is going to pick out a phase and thereby effectively break the symmetry. And as a result, you have photons acquiring an effective mass via the Anderson-Higgs mechanism. Consequently, magnetic fields become expelled, and you get the Meissner effect. And you get lossless flow of currents without any resistance that can persist indefinitely. And it's like pretty crazy stuff. So, but that's like the exception that proves the rule, right? So if we've seen how local phase symmetry blossoms into electromagnetism, you can understand how breaking local U1 phase symmetry is going to break electromagnetism, and you can do a lot of cool stuff with that. So we'll talk about that in a future video, and we'll explore symmetry in superconductors. And then going the other way, as it turns out, our universe is kind of broken because the U1 symmetry of electromagnetism is just a fragment of a more primordial, more general symmetry that electromagnetism used to have back in the good old days. By good old days, I mean the first picosecond after the Big Bang, before the Higgs field went and took on a non-zero VEV. Well, anyway, ever since then, it's sort of like our entire universe has been 75% superconducting, and a superconductor gets you the final 25% to become 100% superconducting. But the 3/4 superconducting nature of our reality is manifest in the fact that 3 of the 4 original electromagnetic, or technically electroweak bosons, have now acquired mass in much the same way that photons acquire mass in a superconductor. And so those are now known as the W and Z bosons that mediate the weak nuclear interaction. And meanwhile, the photon, which escaped mass-free from the Higgs field, is now, responsible for electromagnetism. So that's a trip. Turns out electromagnetism and the weak nuclear force are really 2 sides of the same coin. But that's a story for another day. But it's definitely fascinating, and we will return to that topic someday. Hey, one more philosophical thing I want to leave you with is when we add local phase symmetry to the laws of physics, epistemically, are we adding something or are we taking something away? Right? The burden of these ideas, the structure that we're taking for granted, does that grow as we put in the symmetry, or does it shrink? Does our model become more contrived or more elegant? Honestly, I have no idea. I don't know. And think about that for a while and you'll realize, wait a minute, symmetry, redundancy, active, passive transformations, what is going on here? Like what? And that indeed is the question. What, even is going on here in this universe? Will we ever know? Hey, thanks for watching. I really appreciate it. This YouTube thing has been a lot of fun, so thank you all who have been involved. Shout out to my supporters on Patreon. Really grateful for all of you. And I hope you all learned something today, and I hope you all had a great time. So have an awesome day, and I'll see you in the next one.